Distinguished guests and dignitaries, ladies and gentlemen, Namaskar and a very good afternoon to all of you. On behalf of the Center for Development of Telematics, CDOT, the premier telecom R&D center of the Department of Telecommunications, Ministry of Communications, Government of India, I welcome you all to the webinar on quantum communications. This webinar is being organized as part of the Azadi Ka Amrit Mahotsav, an initiative of the Government of India to celebrate and commemorate 75 years of progressive India and the glorious history of its people, culture, and achievements. This will further the realization of Honorable Prime Minister's vision of building Atmanirbhar Bharat and empowering Gati Shakti to boost multimodal infrastructure connectivity and drive economic growth in the country. The webinar will make the participants take a deep dive into the exciting world of quantum communications amid insightful talks by eminent field veterans. We are privileged to have the gracious presence of Professor Anirban Patak, JIIT Noida, and Professor Soumitra Kumar Sanadhya, IIT Jodhpur, in today's webinar on quantum communications. We would also witness CDOT's group heads briefing the participants about CDOT's R&D endeavors in the areas of quantum key distribution and post-quantum cryptography. We extend our warm and gracious welcome to our expert speakers who are widely acclaimed for their great erudition in their respective areas of research. Ladies and gentlemen, we have the pleasure of the gracious company of Dr. Rajkumar Upadhyay, who is currently the Executive Director, CDOT. Prior to his appointment in CDOT, Dr. Upadhyay has worked in Prasar Bharati as its South Head, Deputy Director General in the Department of Telecommunications, Advisor in Telecom Regulatory Authority of India, TRAI, and in various capacities at BSNL. Dr. Upadhyay holds a PhD in Corporate Strategy and Policy and Masters in Business Administration from Indian Institute of Management, Bangalore. He's an MTech from IIT Roorkee and holds a certificate in International Public Policy from Syracuse University, USA. He's a recipient of several prestigious awards, including J.C. Bose Award by the Ministry of Defense, National E-Governance Award by the Government of India, CIO 100 Award by the International Data Group, and Deepak C. Jain Award by IIM Bangalore. Sir, may I request you to kindly inaugurate this Azadi Ka Amrit Mahotsav webinar on quantum communications and deliver the opening remarks. Sir, please unmute yourself. Yes, sir, you're audible, sir.
Okay. Good afternoon, everyone. Professor Soumitra Kumar Sanadhya ji, Professor Anirban Patak ji, distinguished participants from academia, industry, government, my colleagues Dr. Pankaj Darela, Atul Gupta, Prashant Chuk, ladies and gentlemen. It's indeed an honor and great privilege to be amongst highly august gathering who have joined this seminar or webinar, I say, on this important topic, quantum communications. CDOT is a premier telecom R&D center of Department of Telecommunication, Government of India. It has been widely known for its monumental role in ushering the indigenous telecom revolution in the nation. CDOT has been instrumental in making India achieve greater self-reliance in telecom technologies, as well as promoting local manufacturing of the telecom equipment in the country. At CDOT, we have been working on various technologies like 4G, 5G, both in the area of developing 4G, 5G core as well as RAN. We have been working in optical technologies. We have been working on Wi-Fi technologies, cyber security, ITU cap-based disaster management solution, AI technologies, network management solutions, telecom applications, and so on. In fact, many of our products and applications are already deployed in the field. In line with the clarion call of Atmanirbhar Bharat given by our Honorable Prime Minister, clearly CDOT is at the forefront of making India self-reliant as far as the telecom technologies are concerned. It is indeed a matter of great pride that CDOT has ventured in the area of quantum communications and has achieved considerable success in the same. Quantum technologies are one of the most advanced research areas at present. It is certainly an upcoming and important area that will have great impact on many sectors and economy as a whole. Quantum technologies have implications in virtually all the areas, like provide an exponential increase in computational speed for certain problems once quantum computers come, the ability to break classical crypto systems, high degree of information security guaranteed by the laws of physics, improved sensitivities, accurate measurements, improved atomic clocks, design and discovery of new drugs, new chemicals, financial market, genetics, and host of other areas. And therefore, given the importance this area holds for future, huge investments by governments all across the globe, not only governments, in fact, by private sectors ranging from multinational giants to startups, these investments are being done to be ahead in the technology life cycle. We lost many of the races in certain technology, and this is a good opportunity for all of us to be ahead in this particular technology of quantum communication, quantum in general. I mean, quantum computing, quantum sensing. Many countries have dedicated programs for furthering research in this area, which yield immense potential. In fact, impact of this can probably be compared with that of semiconductor technology in the last few decades, or the impact that the laser has had since its inception, invention in 1960s. Quantum technologies can broadly be divided into four verticals, like quantum computing, which is related to computational power, quantum communications, quantum sensors, and quantum materials. To comprehensively address all these verticals and leapfrog India in this crucial and niche area, India has launched National Mission on Quantum Technologies and Applications, popularly known as NMQTA. In fact, this was announced by Honorable Finance Minister in her budget speech delivered in February 2020. This initiative, with a budget of more than $1 billion spanning over 8 years, is being led by Department of Science and Technology. This program will have active participation from various ministries like Department of Telecommunication, our parent ministry, Department of Space, Department of IT, MIT, Department of Atomic Energy, and so on. As far as the CDOT is concerned, out of the four verticals where quantum research is being undertaken by various organizations in the country, we at CDOT are working in the area of quantum communication. Government has mandated that CDOT functions as technology hub for the country in the area of quantum communication. As per most of the security and cyber security experts and cyber cryptography experts worldwide, quantum algorithms running on quantum computers will become potential threat to all the communication systems that are dependent upon the current cryptography techniques. In order to avoid and protect our critical infrastructure, from attacks, which will be possible because the power of quantum computers in the coming years. I mean, from the perspective of developing cryptographic solutions that can overcome the breaking power of quantum computer, CDOT has already started working at the forefront of developing quantum safe technologies for the future. These technologies include quantum key distribution, popularly known as QKD, and post-quantum cryptography, PQC. While the former is based on quantum physics, the latter is based on newer classes of hard mathematical problems. I'm really happy to inform that CDOT is not only at the forefront of developing both QKD and PQC technologies, but also combining these technologies to achieve the best-in-class cryptography solutions for communication security for the government, as well as financial institutions, strategic agencies, and host of other end users who find application for these technologies. While CDOT has been having good expertise in developing practical solutions in these upcoming areas of quantum communication, we also understand that these kind of areas will require strong theoretical foundations as well. Therefore, CDOT from the very beginning is having an excellent collaboration with top-class academic researchers in this field. We have set up an advanced lab on quantum communication in CDOT Delhi that was recently inaugurated by Digital Communication Chairman and Secretary Telecom on 9th of October. This lab augments the existing lab on post-quantum cryptography in CDOT that is developing QKD and PQC based products. With this lab and commitment from our greatly motivated researchers, CDOT is poised to take a big leap in the futuristic area of quantum communication and quantum cryptography and emerge as a leader in R&D of indigenous technology in these areas. Since the general awareness of quantum technology is rather limited because it's a quite new area, this webinar is timely so that more and more professionals are exposed to this niche area. I look forward to enlightening talks by two leading experts of international repute, Professor Anirban Patak and Professor Soumitra Kumar Sanathia, who are going to deliver talks giving overview of quantum communications and post-quantum cryptography, respectively. It is my firm belief that these talks will kindle interest in this important area, and participants of this seminar will continue to pursue that interest in future as well. I hope all participants will make full use of question and answer session to get their queries resolved. CDOT also invites other organizations working in this area to collaborate with us and synergize their efforts with CDOT so that duplication of activities is avoided and we deliver together as an ecosystem great solutions for our country. And this is also very, very essential to quickly develop products and solutions in this area. Because as you are aware that many countries are working in this field, and definitely there will be first mover advantage which can be built upon with the initial success. There is also a greater need for academia and industry to join hands, as domain experts are rather limited in this area. Technology is still considered at the stage of infancy. Through this webinar, through this forum, I'm also extending our offer from CDOT to the startup community to come and carry out research in CDOT. We'll provide you all the facilities, all the support, all our access to our labs to carry out research using CDOT's facility. I'm sure this webinar will be of great help to people who are looking research in this area. I wish this webinar a great success. I hope you have a great time in this seminar. Thank you so much. Kumar, over to you.
Thank you, sir. Thank you, sir, for inaugurating this Azadi Ka Amrit Mahotsav webinar on quantum communications and briefing us about the critical relevance of quantum technologies and their upcoming applications. We are graced by the esteemed presence of Professor Soumitra Kumar Sanathia, who is an associate professor in the Department of Computer Science and Engineering at IIT Jodhpur. Before moving to Jodhpur, he has served in IIT Ropar, where he was head of the CSE department for 2 years. He obtained his BTech degree from IIT Delhi and PhD from Indian Statistical Institute, Kolkata. His research interests include design, analysis, and efficient implementation of cryptographic algorithms and protocols. He has been working with many Indian governmental agencies and corporations in the field of cryptography and cybersecurity. He has been a popular teacher and likes to teach courses in the domain of cryptography, theoretical computer science, and mathematics. He has received Best Instructor awards twice in the past. Currently, he is also the coordinator for a cybersecurity certificate program being run by IIT Jodhpur. It's our pleasure to have you here, sir. Sir, may I request you to deliver your talk on post-quantum cryptography?
Thank you very much. Thanks, Dr. Upadhyay, for very enlightening comments about the importance of post-quantum and quantum communication, post-quantum crypto and quantum communication. It's my pleasure to deliver this talk in CDOT. Let me share my screen.
So you can share your entire screen, because if there are animations in the presentations, they would not run properly.
I hope you can see this already.
So it's not. Yeah, sir.
Okay, thanks.
Yeah, so we are able to see it.
Okay.
Sir, before you start, Aman, you can announce how you can maximize the presentation. You can, some of the users may be new to the tool.
Yeah, so we will minimize it from here.
Aman,
okay.
Can you, sir, I just wanted to tell the participant that if they want to enlarge the presentation, there is a button right side which can enlarge the presentation to full screen mode. Thank you.
Thank you. And it's my pleasure to deliver this talk on a very timely topic of post-quantum cryptography. And it's actually a pleasure to know that CDOT is already doing a lot in this area. And more importantly, it is not just an interest for an experimental knowledge, but actually to implement these ideas in products. This is rare to see in Indian organizations, and I'm extremely happy to know that CDOT is actually taking lead in this domain. So today's talk, I will talk about post-quantum cryptography. I will explain what do we mean by post-quantum cryptography, and I describe some of the techniques of post-quantum cryptography. And since I'm not an expert in every area of PQC or post-quantum cryptography, I will spend a little more time on some of the techniques, and will skip through the details of some others. So, okay. So the content in these slides is taken from various sources. So first of all, I would thank my wonderful and very talented PhD student, Amit Kumar Chauhan, who has been involved with me for a long time. And in fact, I'm proud to have students like him with whom I got an opportunity to work. We have worked on many topics, including post-quantum cryptography, as well as techniques of how to utilize quantum methods for breaking symmetric encryption algorithms. This is the topic on which I am currently working with him, and he is making wonderful progress in that area. And then there are well-known and established researchers like Luca Di Fio, Nicolas Andrea, Holman, Mike Hamburg, etc., whose slides I have used in preparing this, and I would like to thank them here. So, as you already know, cryptography is related with the art and science of secret communication. So the crypto means secret and logos means science, and together it means essentially the science of secret, or in general secret communication. But this was the original name given to the subject when it was primarily used by militaries and diplomatic missions only. But slowly cryptography's usage has expanded to many different areas and multiple aims, not just secret communication. For example, you can even try to prove a statement to somebody without telling how the proof works. And this is a very interesting idea. When the paper on this topic was written in 1985 or approximately then, people didn't realize how practical this could be. It was just treated as a theoretical discussion. But today you see a Bitcoin, which not Bitcoin, a cryptocurrency called Zcash, which heavily makes use of this construction called zero knowledge proof. So I'll come back to secret communication for most of this talk, but just wanted to let people know that this is not the only area for cryptography. Cryptography has expanded tremendously to multiple domains. So as you can imagine, cryptography is concerned with locking of a message. So the sender locks the message somehow by using some cryptographic technique, and this message reaches the receiver, who can somehow unlock this and read the content. The interesting property which is given by this lock is that anybody who is listening in between, some eavesdropper, cannot understand what is the content of the message. And till 1976, the only way to do this was to actually apply an algorithm with the same secret key on both sides. So party A and party B, traditionally called Alice and Bob in crypto literature, when they want to talk to each other, they would have the same secret key K on both the sides. And this was known as symmetric key cryptography for this reason, because the key was symmetric on both sides. However, the situation changed towards the late 70s. Whitfield Diffie and Martin Hellman wrote a paper called New Directions in Cryptography. And there they actually created a technique in which secret data could be exchanged between two parties while they are talking publicly. And this was an amazing result for that time. Before this, nobody could even think of how to create a secret between two parties who do not have a secret channel between them. They're talking publicly. There are listeners who are listening to every message passing between Alice and Bob, and yet at the end of the protocol, Alice and Bob will share some secret data, while others who are listening in between will not be able to compute it. In fact, the authors knew what they were doing because they titled their paper as New Directions in Cryptography, and the first sentence of this paper was, "Today we stand on the brink of a new revolution in cryptography." So they knew that they were creating a revolution in 1976. The technique that they created was based on solving the discrete log problem in certain algebraic groups. However, they couldn't really create an encryption scheme. So the idea they suggested in their paper is that now Alice and Bob can communicate publicly, generate a secret key, and then use this secret key for any symmetric key crypto system. But can somebody encrypt with just some public information and no secret communication between the two parties? This remained an open problem in 1976. And publicly, this was solved for the first time in 1978 by the famed trio of RSA, or Ronald Rivest, Adi Shamir, and Leonard Edelman. And they created a method which is now known as initials of their names as RSA encryption algorithm. Now we know that the same kind of almost similar system was already invented by Clifford Cox in British Secret Service a few years before the RSA invented it. But publicly, nothing was known about it. So the first public method which could use encryption with just public information exchange was this RSA. And this is based on hardness of another number theoretic problem, which is quite related to factoring but not equal to. So if you can break the RSA scheme, then it is not guaranteed that you are allowed to factor very large integers. But if you can factor large integers, then you can certainly break the RSA scheme. So this the scheme is securities relies on a problem which is very much related to factoring large integers. And in some groups, it has been proven that under certain assumptions, factoring is equivalent to breaking RSA encryption algorithm. And this is what is primarily used on internet today. And of course, these and another variant which can be created based on the work of Diffie and Hellman. And the technique which was created is by an Egyptian mathematician, Tahir al-Jamal, and who created what is known as al-Gamal encryption system. And then there are a few more variants of RSA and based on new problems like quadratic reciprocity and so on. But all of them are based on certain mathematically hard problems which are based on either some finite groups or based on number theoretic assumptions like factoring. Around the same time, a few years after these papers were published, a conference took place in MIT in 1981, and the conference was on physics and computation. No. So physicists were already starting to get interested in the nature of computation given only the laws of physics. And in this conference, this is just a screen grab of the previous picture, where we just put the names of the people who were attending. You can see a few Indian names also, Tyagarajan and Gupta there. But the most important people for our work here is Feynman, Richard Feynman. And Richard Feynman published a paper in this conference where he talked about simulating physics with computers. And these are few sections of that paper which highlight some very important and fundamental questions that he asked. So he asked in particular these 4 questions. Can classical physics be simulated by a classical computer? And this led to discretization and probabilistic laws of nature. The second question he asked was, can quantum physics be simulated by a classical computer? And he could show that it is not feasible. And this showed a separation between classical and quantum computation. So whatever can be done by a classical computer can certainly be done by a quantum computer, but the reverse is not true. So the quantum computer may be more powerful than classical computer. Another thing that he asked, and a very important thing, was can physics be simulated by quantum computer? And this led to the foundations of what we today see as quantum computers, or how to build quantum computers. And then the fourth question he asked was about the nature of computing, and this was, can quantum simulation be universal? So he was talking in universal in the sense of universal Turing machine, and this led to the foundations of the theory of quantum computation. So for our purpose, we are mostly interested in the existence of quantum computers, which was predicted by Feynman already in 1981. However, significant work in this domain started only in the 90s. Peter Shor came up with an algorithm in 1994, and this amazing paper showed that if you have quantum computers, then the factory problem as well as discrete log problems will become very simple to break. In other words, they will be solvable in polynomial time in the length of the input. And if that happens, then the security of all popular asymmetric crypto systems like RSA, digital signatures algorithm, Diffie-Hellman, they will all become insecure. A few years later, Love Grover, who is a BTech student from IIT Delhi, apparently from the same hostel where I stayed in my BTech, Kumar hostel, but much senior to me, he came up with a wonderful result in 1996, and he showed that even if you have an unordered data set of n elements, which traditionally on a classical computer will take time order n, because the only way you can search for a particular item in an unordered database is to go through the list one by one. So if there are n elements in the database, you will need to try roughly n times. But what Grover showed in 1996 is that if you have a quantum computer, then you can search for a particular data you are looking for in the database with an effort which is only big of under root n. And this quadratic speed up is a tremendously powerful technique which can actually be used to break even the symmetric key crypto systems. So the public key crypto systems that were known till that time were broken by Shor, and the symmetric key crypto systems were made weak by Grover. And then there is a similar problem which is by Simon in 1994, and which can find hidden period in polynomial time. And in recent years, this paper has been used in re-evaluating the security of Weistel-based constructions, Ivan-Minsu cipher, and so on. So, but the main point that I want to say about this slide is that these two papers, the Shor and Grover, they had a fundamental impact on cryptography. Shor said that the kind of public key encryption techniques which were being used till now will all be broken if quantum computers of a certain size are available. And Grover said that searching for a secret key in among a huge number of secret keys is going to be achievable with only square root time in the size of the input. So the first one, the first result broke the public key, and the second result had not really a complete break, but an impact on the secret key techniques also. So in the symmetric key or the secret key techniques, if we had a key of size 128-bit, Grover's method would allow somebody to search this secret in an effort which is only 2 to the power 64. And that's an amazing result. The only way you can counter this is to actually build encryption schemes which are double the key size of the level of security you are looking for. So if you want a security of 128 bits and you want to resist Grover's algorithm, then you need to use secret keys of size 256 in practice. Because 256-bit key when searched with Grover's algorithm will still take 2 to the power 128 effort, and this is the security level that you are aiming for. Now we come to the idea of post-quantum cryptography. This term was coined by Dan Bernstein in US, a very famous cryptographer and the inventor of some of the techniques of post-quantum cryptography. And the idea of this term is that you build cryptographic schemes which will remain secure even in the presence of quantum computers. And then we can talk about what do we mean by the kind of power a person has when somebody has quantum computers. So we have 3 models of quantum computers. In the first model known as Q0, the attacker is only going to look at the encryption and decryption functions as which are mentioned here as oracles, only in the classical sense. So the questions will be asked to encryption and decryption oracles only in terms of individual encryption and decryption queries. And the attacker can only make classical computations. Now we come to Q1 model. In the Q1 model, the attacker can still make only classical queries. So encryption decryption queries are still going to be only in a classical sense, in a normal computer which we have today. But the attacker is now allowed to do offline quantum computations. Because he or she has the quantum computer, they can now do some search or some computation on this quantum computer. And this is of course slightly more powerful than the Q0 model. And the last model we have is Q2, which is the most powerful model. In this model, the attacker can actually make superposition queries to this encryption and decryption oracles and can also do quantum computations. And in these 3 models, people have tried to see how cryptography schemes can be designed. And mostly we are looking for Q2 model because this is the highest level of security we can think of. So even when somebody is allowed to make quantum superposition queries and perform quantum computations, you can still not find the secrets hidden in the encryption and decryption algorithms. So NIST, the US Standards Organization, has started a standardization process for developing PQC algorithms. In February 2016, they started this competition. And in December, they published a formal call for proposals, which focuses on key encapsulation mechanisms and signatures. I'll mention what they are very soon. And the deadline for submission of the competition was November 2017. There were 69 candidates which were submitted by some industry and academic people. And in December 2017, this list was published, which is known as the first round of PQC competition. In the second round in Jan 2019, last year, out of these 69, 17 candidates were selected for public key encryption and key encapsulation mechanism candidates, and 9 were left for digital signatures. And in July 2020, which was the third round, NIST announced 4 finalists and 5 alternate candidates, plus 3 finalists and 3 alternate candidates for digital signatures also. If you want to see more about it, then there is a page of NIST which you can look at it, given at the bottom of this page. Now let's come to what is public key encryption. So in the public key encryption, here are the 2 people, Alice and Bob. So Alice sets up a public key and secret key using some key generation algorithm and sends this public key to Bob. Now Bob has a message M which he wants to send to Alice. Bob encrypts with the public key. Bob encrypts this message M with the public key by using a functionality called encrypt and produces a ciphertext CT. This ciphertext is transferred to Alice, who can now use her secret key SK to decrypt this ciphertext CT and obtain the message M which Bob wanted to send. In the I just mentioned about the key encapsulation mechanism. In the key encapsulation mechanism, we make a slight change in the idea. Now we are not going to use the traditional public key encryption like previously. One of the reasons is that public key encryption is very, very slow. So what we want to do is we want to do a key exchange somehow using this public key ideas, but then start using symmetric key for encryption and decryption. So here, again, like previously, Alice sets up a key gen algorithm and produces public key and secret key, sends the public key to Bob. Now Bob runs an algorithm called encapsulation, which only takes the input as public key and produces a ciphertext and the secret key K. The key K is kept by Bob with him, and the ciphertext CT is sent to Alice. Now Alice has a corresponding function on her side as well called the decapsulation mechanism. She runs this decapsulation mechanism function on the ciphertext CT with her secret key SK and obtains the same key K. So you can think of it as a key exchange function. And once you have exchanged the key, now you can use a symmetric key algorithm to speed up the process of encryption and decryption. The final thing that we mentioned already in the NIST competition is about signatures. So signatures are methods where you can verify the correctness of a document coming from somebody. So as an example, Alice wants to send a document containing the message M to Bob. But there is no guarantee that Alice sent this message, because if you simply encrypt it, then public key of Alice is public, everybody knows it. So anybody could have encrypted any message of their liking with the public key of Alice. And therefore, it is not clear who sent this message. Now, what we want to know here is that Alice sent this message M to somebody. And this is achieved by what is known as signature scheme. So what Alice does is a reversal sort of a thing to what encryption was doing. In encryption, you were taking the public key for encrypting and looking at symmetric key to decrypt it. Here, to create a signature on a message M, Alice chooses her secret key, creates a signature called sig, and sends the message and the signature to Bob. Now Bob can actually verify with just the publicly available information, which is this PK, that the message M has indeed been signed by Alice, or in other words, actually by Alice's secret key, which is only supposed to be known to Alice. Now we come back to the real PQC competition. So PQC competition relies on some problems which are very, very hard even for quantum computers. So even if we have a very large scale quantum computer, we cannot hope to break certain problems. Just like in the classical sense, if we do not have a very large scale classical computer, we cannot break factoring problem, we cannot break the discrete log problem in certain groups and so on. And on the basis of these, we could create very nice encryption and key exchange algorithms. In the same manner, in the post-quantum era, when quantum computers of very large scale will be available with people, we still want to have encryption and decryption security. And this is possible only if we have problems which are going to be hard for quantum computers to solve. Because if quantum computers can solve every problem, then no matter how you create encryption and decryption functions, they will be broken by quantum computers. So we have a category of problems. These 5 are the prominent ones which are used today. The first one is lattices, the second one is coding theory, the third one is based on cryptographic hash functions, the fourth one on multivariate equations, and the fifth one on isogenies. So I'll mostly talk about the first two, and I don't think I will have time to describe the remaining 3. Even in the first two, I will try to be short and try to give you an overview of what the problem is and how do we get an encryption or signature scheme out of it. So a lattice is nothing but an additive subgroup of R to the n. So in this picture, you can see a very neatly arranged set of points in 2 dimensions. So a lattice is nothing but similarly neatly arranged points in multiple dimensions, in particular in dimension n. So if you want to describe this neatly arranged points, then we need a basis vector. So this basis vector essentially are those vectors whose linear combinations will be able to give you, whose integer linear combinations will be able to give you all the points in this structure. So given basis, we have a unique lattice, and given lattice, we have multiple bases. But the number of elements in each of these bases is going to be constant. Now there are some lattice problems which are very hard. Ideally, we want to do cryptography, we want to do average case problems, which are hard on an average. So we do not want to have problems which are extremely hard for quantum computer only in the rare case of the hardest situation. So the hardest problem may be very, very hard, but on an average, somebody can solve the problems very easily. Then you cannot build cryptography out of it. To build cryptography, we need an average case hard problem. So if we have an average case hard problem based on lattices, then we can build post-quantum secure encryption algorithms. And indeed, we have such problems. 2 such problems are listed on this slide. The first one is called SIS, or small integer solution problem, and the second one is called LWE, or learning with error problem. So the SIS problem allows us to build one-way functions, collision-resistant hash functions, digital signatures, and identification schemes. And LWE problem allows us to build encryption, oblivious transfer, identity-based encryption, and hierarchical IBE. If you look at the worst case problems, there are these 2 which are called SIVP and BDD, and there is a quantum reduction between the 2. So quantumly they are identical. So if you can break SIVP, then you can also break BDD, and if you can break BDD, you can break SIVP. So in some sense, they are identical level of hardness. However, the problem with these problems is that they are hard in the worst case, not in average case. And this is why we build encryption and signature algorithms based on this average case SIS and LWE problems. The arrows in this slide show the reduction proof, which means if I have a solver for SIVP, then I can break the SIS algorithm. But we know that this SIVP problem is in the worst case very hard, and this actually proves that SIS in average case is also hard. So let's look at the SIVP problem. The SIVP problem says that given a lattice, you have to find n short and linearly independent vectors. So linearly independent vectors will be what will form basis, and by short I mean that I want to reduce the norm of these vectors by to a small upper bound. And this problem is known to be hard even for quantum computers. The other problem, BDD, which I mentioned, is as follows. You are given a lattice and you are given a target vector. You have to find the point which is closest to this point. The red colored point here, you have to find which is the closest point in the lattice for this. And by closeness, you are normally measuring the Euclidean distance. And even this problem is quantumly very, very hard. Now I come to the 2 problems, SIS and LWE. So the SIS problem is that when you are given some m vectors, each of length n coming from a group or a field ZQ, your aim is to find out linear combination of these vectors so that you can get a 0 vector. So finding linear combination of given vectors to obtain 0 vector is in general not a very hard problem. You can use Gaussian elimination to solve this problem. But this becomes extremely hard if we restrict these linear combinations to only certain values. So these red colored values Z1, Z2, Z3, Zm, if you don't restrict them, then it's a very easy problem by Gaussian elimination. However, if you restrict these Zi's to only these 3 values -1, 0 or 1, then it is extremely hard, even for quantum computers. And now I come to the LWE problem, based on which I will try to describe at least one technique of encryption. So we talk about a large matrix A, which is containing m rows and n columns. Each of these rows is nothing but a vector of dimension n, and these vectors are what A1, A2, A3, Am are. Then we keep a secret key S, multiply this matrix A with the secret S. The secret S is of size n by 1. It's just a column vector of length n. So when you multiply this matrix m by n, dimension m by n, with this column vector n by 1 size, you will get an m by 1 vector, or a column vector of length m. To this we can add a small error. This error vector is shown by this purple colored column vector E here, and this everything together produces what is the final value B. Now LW says that given the matrix A, which is what I showed in the previous slide as this containing these various rows of A1, A2, A3, etc. If you do not know the secret S, then somebody who gets the input A and AS plus E for some random choice of S and E versus somebody who gets the vector A and a completely random vector B, not computed by this construction shown in this picture here, then the attacker will not be able to identify which one is the input, whether the attacker got the value AS plus E or the attacker got the value B, which is randomly chosen. You will not even be able to identify. And this problem is known as learning with error problems. Now using this, we can actually create encryption schemes. And the idea is very simple. You take a single bit which you want to encrypt. For each bit that you want to encrypt, you generate a random vector of length m and pre-multiply it with the matrix R. So you will create this value R times A. And then for the same vector R, you also do this R dot B, the dot product of R with the vector B, and add to it Q by 2 times the number Z that you want to encrypt. Number Z is either 0 or 1. It's a 1-bit thing that you want to encrypt. Q is an integer. So Q by 2, I mean, essentially we are looking at the integer part of Q by 2. And you send these two things to the recipient. Now the recipient, by given these two things, will be able to identify what Z is. And the way the recipient will work is as follows. The recipient will get two inputs U and V, where U is supposed to be R times of A and V is supposed to be R dot B plus Z times of Q by 2. So the recipient will compute the inner product of U and S, the secret key S, and subtract V from it. As you can see from this computation, if you look at U dot S minus V, then this comes out to be equal to R dot E minus Z times of Q by 2. But we already said that E is an error vector which is very small in size. Each of the quantities in the error vector, each of the components is very small. And therefore this R dot E is going to be much less. And this is going to be dominated only by the second term. So if Z is 0, then you will get U dot S minus V to be a very small quantity. And if Z is 1, then you will get U dot S minus V to be a very large quantity. And that is enough for us to decrypt. So very interesting idea based on the LWE problem, but it only works on a single bit. So you want to look at the way encryption happened. The matrix A was randomly generated and probably very huge. So you want to reduce the size of this public key. So there was another construction called ring LWE. In the ring LWE, the matrix A is not generated from completely from random, but it is generated from a seed. And you only need to send that seed to the other side, and the other side can generate the same matrix. However, the quantity B, which is A times of S plus E, is still somewhat large. and you need to do a full matrix computation, full matrix multiplication to compute the vector B. So the idea of ring LWE is that don't use a random matrix A, but use a matrix with a very strong structure inside it. So you see a matrix C here, which is cyclic matrix. If you are given the first row, you can actually obtain the second row by just shifting by 1. And you can obtain the third row by shifting by 2, and so on. If you have such a matrix, then you only need to send the top row, because remaining rows can be computed very easily. Not only that, for the top row, you can associate a polynomial by this function written there. And this polynomial allows us a very efficient matrix multiplication, which is called entity, number theoretic transform. And this entity is nothing but a fast Fourier transform when applied to finite fields. And this makes the encryption function much practical. However, the trouble is that this may not be secure, because this structure which you have utilized to make it fast might also help the attacker. In fact, we have one of the competition entries in the NIST competition based on this ring LWE, and that scheme is called New Hope. It was even tried by Google for a few months on their platform. So they encrypted their communication using this New Hope algorithm. So if you want to, you still want to retain the advantage of fast encryption and decryption, and the key size to be small. But the trouble is that this module is very large. I mean, the matrix was very large, and to make the structure, when we did something, then it could be weaker in security. So a newer idea, which was pioneered by another technique called Kyber, again a very strong entry in the competition. What they did is they didn't take off a matrix A as just a circulant matrix, but they looked it as a multiple blocks, and in each block you had circulant matrix. Now, this probably gives you a feeling that the size of the public key will still be very large, because now you are using large number of blocks, and in each of these blocks you are putting a circulant matrix. But note that each of these circulant matrix is also of smaller size, and that makes the public keys to be almost the same size as in normal LWE based encryption schemes. And then what I want to say is that this is very fast and simple. The only trouble with this lattice based encryption schemes is that the keys are large and the ciphertext is also large, but they're very good for applications like TLS, like key exchange and encryption. And there are some specific examples, like Entru is time tested. It's a very old scheme, has not been broken yet. Saber is a very simple scheme in this class of algorithms. Kyber has good all-around balance. Frodo is based on standard LWE, but this is very large and a very conservative option. So I'm not sure if I have time to discuss more about code-based cryptography, but I'll just mention the idea of code-based cryptography in 1 or 2 minutes. That is, in coding theory, we study these kind of problems when you have a data and you just expand it by using some kind of a coding theoretic mechanism, so that the code word becomes a larger size. And then somebody can do small errors in this code word, and yet, as long as the errors are small, you can decode and obtain the original data back. And there are some classical results by Shannon, etc., which show that decoding probability is close to 1 if the errors are not very high. Now, random errors are actually known to be very hard to remove. There is a classical result from 1978 by Berlecam, McAleese, and Tilburg, which says that even if you have very small amount of error, it is extremely hard to remove it. And this problem is actually hard even on quantum computers. So what coding theory does is, coding theory or the techniques as we are going to use in cryptography will be as follows. You will take a plain text, you will expand by using some code word, and here you will intentionally add some errors. The point of intentionally adding errors is that somebody who does not have a suitable structure of the code word used will not be able to decrypt and obtain the decoded input. But if somebody knows the structure of this code, which is underlying the mechanism, then he or she will be able to remove this error and obtain the plain text. And this is exactly what is done in code-based crypto systems. So there are the classical example of code-based crypto system is from Michaelis in 1978, and surprisingly, despite being given in 1978, this has remained secure till today. It is based on binary Gopa codes. People have tried to make it faster or reduce the size of the key smaller, and they have done things like this. People have used read-solvable code, concatenated codes, rank metric codes, and so on. But many of them have been broken by researchers. However, Michaelis remains strong till date, even from 1978. And then there are some MDPC codes and rank metric codes which have also not been broken, and schemes based on these has been built in post-quantum crypto computation. So I don't think I have time to describe more of the schemes. So I would like to stop here and maybe hope for would be happy to answer some questions. Yeah.
Thank you, sir, of sharing with us the intricacies and nuances of emerging cryptographical landscape in such an elaborate and meticulous manner. Sir, due to paucity of time, will not be able to take questions. We'll mail them separately to you.
Thank you. Thank you very much. Thank you.
We are indeed privileged to have the gracious presence of Professor Anirban Patak, who is a theoretical physicist. He did his PhD from Vishwa Bharati Shanti Niketan. Subsequently, he was a postdoctoral fellow in the Freie University, Berlin. He joined JIIT Noida in 2002. At present, he is actively involved in teaching and conducting research related to several aspects of quantum optics and quantum information with a focus on quantum cryptography. He is a fellow of the National Academy of Sciences, India, and Institute of Electronics and Telecommunication Engineers, IETE. He is also an associate editor of Quantum Information Processing Springer. He is a recipient of the 2017 Sriyatul Bhasin Award in the field of electronics and information technology. Sir, we look forward to learning from your wide knowledge in the era of quantum communications. Sir, may I please request you to deliver your talk?
Thank you for the introduction. I hope I'm properly audible.
Yes, sir. So you may please share your screen.
So does not it allow the share only the file, means it shows only the entire?
It does. Yeah, sir, it does. If there are any animations in your presentations, they would not be visible to all. So if the presentation does not have animations, then maybe you can upload the presentation, or we would recommend you to use the screen share feature. So you can find the option of share screen. Yeah, sir. It is started, sir.
So you can see my slides now.
Yes, sir.
I just wrote the slides.
Yes, sir. We are able to view it properly.
Okay. So I'll start, and if you have any question in between, also you can stop me instead of waiting till the end. And so that, as I have been asked to be lucid and keep in mind that there may be audience from varied expertise, means, so I'll not speak about much more mathematical things, means, but I'll try to give the perception of what is happening all over the world on quantum cryptography, and more it's about quantum communication. So there are two aspects of quantum communication. Sometimes it involves security and sometimes it does not involve security. So I'll touch upon both the aspects. So in the top, in the first slide, what we show is China to Austria communication that has happened with the help of secure quantum key. So the role of the satellite was to establish the key, and then the encrypted video conference happened between the China and Austria, and this was the most discussed thing that has happened ever in quantum cryptography. So we'll come to it with some more detail. And in the bottom, what we are showing is a Clavis 3. This is a commercial product that's ID quantic cells, and there are many interesting things happened about this, but the most interesting thing is probably will come after my talk, that now there can be a indigenous technology, and even CDOT is planning to make a commercial product which will have a cryptographic solution, commercial cryptographic solution. So at the moment, this Clavis 3 is a very popular commercial solution. So in right, it shows that we all know about Alice in Wonderland. So now Alice and Bob goes to Quantum Land, and in next few slides we'll explore what happened there. So let us also go there. So before I go really to the quantum world, so I start with a bit of history. So somewhat my previous speaker also introduced you to the history. So and a bit of connection to India, that Law was a student of IIT Delhi. He was actually born and brought up in IIT Roorkee. His father was a faculty in IIT Roorkee. Anyway, so this is about Bennett and Brassard, whose famous paper BB84 is known to be the first ever protocol of quantum cryptography, but this predates or this owes a lot to Stephen Weisner. So Stephen Weisner was actually Charles Bennett classmates, and they did college together, and then for MS they were in two different cities, and Weisner used to visit very often Bennett, and during one of this there's a discussion, Bennett took this note. So the right hand side is a note Bennett had taken while discussing with Stephen Weisner. So Stephen Weisner wrote a paper with the idea that there will be, instead of the numbers in the currency note or bill, there should be some qubit. But such a qubit is very difficult. You know that now that unknown quantum information cannot be copied. So such a bill nobody will be able to copy. But the problem is that the moment you will try to put it in your wallet, the qubits will be measured and their states will be lost. So you cannot really have such a thing. But that had almost all the idea of quantum cryptography, and he sent it to a journal and rejected. It was in IEEE transactions, but it was written in more in the language of physicists, and it was rejected immediately by IEEE transactions, and it took 13 years for this publication. But in between, so this is published in 1983 and written in 70. So in between, Bennett was very convinced about this idea and told this idea to many people. So there was a conference in Puerto Rico, and there it's a beach town, and in Brassard was swimming, and Bennett went there swimming and told Brassard about the crazy idea of Stephen Weisner, and they discussed all these things while they were swimming. And when they returned to the coast, by then they had the idea for first two papers, but those two papers were written, but it was very difficult for publishing those papers. So then there was a conference in India. So I just quote something from Brassard. So we wrote up a proposal for 1983 IEEE Symposium on Information Theory, which was at Montreal. Not only that was it accepted, but it was granted a long presentation. But there was no official publication. Shortly thereafter, my good friend Vijay Bhargava, so this is the Quantum Cryptography's India connection, was in charge of a special session on coding and information theory in another IEEE conference, which was held in IISc Bangalore in December 1984. He invited me to give a talk on any subject of my choice. And considering how difficult it was to get these ideas published at that time, so now quantum cryptography is so convincing, so much discussed, but at the time it was so difficult that Brassard took this opportunity and published this paper in a conference proceeding, the conference held in IISc Bangalore. So that's India connections and history part of BB84. So BB84 was immediately followed by a couple of other papers. So one of them is, so in what happens in BB84, that Alice prepares states in 0, 1, which we can view like horizontal or vertically polarized states, and 45-degree polarized, 135-degree polarized randomly. So quantum mechanics does not allow me to simultaneously do measurement in horizontal vertical photons as well as the 45-degree, 135-degree photon. So these are like my axes or bases. So if I do a measurement in horizontal vertical basis, then I cannot do measurement in 45, 135-degree. So I'll come quickly to that. So there were actually 4 basis states, 0, 1, plus, minus. The plus is 45, minus is 135. So then Eckhart come up with the idea where there were 6 states, and they used something called entanglement. Then Bennett come back once again with another idea, and Bennett told that neither 4-state nor 6-state is required, 2-state will be sufficient, and then he introduced a 2-state protocol called B92 now, and Bennett was the sole author of that. So later on, so in all this protocol, the security was apparently coming from conjugate coding. So what does it mean? It was coming from our inability to measure simultaneously in 2 bases which are non-orthogonal. So we cannot do measurement in non-orthogonal basis, and security was apparently appearing from that. So it was coming from my inability to measurement in 0, 1 and plus minus basis, or horizontal, vertical and 45, 135-degree basis. Soon, Goldenberg and Wedman come up with the idea using Mach-Zehnder interferometer. I am specifically mentioning Mach-Zehnder interferometer because I will show it. So, which can perform quantum cryptography or quantum key distribution with orthogonal state. So, it established that conjugate coding is not essential. So, what is our main research contributions, or one of the main research contribution of ours, is that to extend it beyond QKD and to establish that not only QKD, any cryptographic task that can be done using conjugate coding can also be done using orthogonal state. So it continued, and in 1999, some interaction-free measurement-based quantum cryptography come in, which is known as counterfactual quantum cryptography, and that's very much discussed at the moment. So up to this, it was only key distribution, and then after a key is generated, which is ultimately a random number, then that key was used for with a classical method. Suppose you have a message A and you have a key B, you just do A XOR B and send it. So such techniques were used where only the key generation part was quantum mechanical, but the remaining communication part was still classical. So in 2002, Bostrom and Feilbinger in a nice protocol called ping pong protocol showed that, well, it is possible to directly communicate or provide direct secure quantum communication. So that communication can be done by quantum means only without prior generation of a key. So key distribution is not essential. You can start from direct communication, and then later on it's generalized to many such things. So now, before we go to such protocol, let's look at even more basic thing. So as I have been told to start from fundamental, so I recall certain things which all of us have read, means independent of whether I was in electronics, I was in computer science, or I was in physics, all of us have read certain things. So the left hand side is showing a Bohr model. So just recall Bohr model. So in Bohr model, there is a nucleus, and then there is a n is equal to 1 energy level, and all the electrons can come from n is equal to 3 to 1, 2 to 1, 4 to 1, and all this creates a set of lines called Lyman series. When it falls down to n is equal to 2, it's called Balmer series. And if each of this level has its energy, so n1 is equal to E1 corresponding energy, n2 has a corresponding energy, E2, and so on. So when an electron falls from EF, F level to EIth level, then the energy difference is EF minus EI, and I divide by H, and that's the corresponding frequency. So I see different wavelength for, that leads to different spectrum. So this is the spectrum. So the whole point is there are energy levels which are discrete. So I can have n is equal to 1, so E1 energy level and then E2. I cannot have an electron in a level which is E1 plus E2 by 2. So that gives me the idea of discrete energy level, and this word discrete means quantum. So quantum means discrete. So this is quantum mechanical. Now you all use laser, and entire classical communications happens with the laser. And this is a semiconductor laser. So even in semiconductor, you see that what is a semiconductor? They have a band gap. So band gap means there is a certain energy level allowed and another energy level is allowed, and in between there is certain energies which are not allowed. So that's what is forbidden band. And if forbidden band is higher or forbidden layer is larger, the gap between conduction band and valence band is higher, then it's an insulator. If conduction band and valence band superposes, then it's metal. So this is also a discretization of energy level. This is also discrete energy level, and so this is quantum. You cannot understand a semiconductor without understanding basic quantum mechanics. And this semiconductor laser has a source, but again, if you look at the construction of laser, that has at least 3 energy level, and one of them are metastable, and so this is discrete energy level. So the point is that the semiconductor, laser, all this integral part of the traditional communication, classical communication, has an intrinsically quantum mechanics, or for a clear understanding of that, you need quantum mechanics. Even the fiber through which you are doing total internal reflection and sending the light. So why the fiber is transparent? Fiber is transparent because the light which is coming does not have enough energy to excite the electron from the valence band to the conduction band. So even the transparency is explained through quantum mechanics. So quantum mechanics is very much present in your classical communication world. However, we don't call them as quantum communication. That means quantum communication also uses quantum properties, but probably some more weird quantum properties. So what are those properties? So to begin with, I talk about qubit. Qubit is the fundamental building block. So if what is a bit? So bit is a 2-level system which is either at 0 or at 1. So if I consider that there is a nucleus and the electron is either at excited state 1 or ground state 0, then it's a bit. Now quantum mechanically it can be in superposition of both. It can be simultaneously in 0 and 1, and then it's called qubit. But there are some more intrinsic property of the qubit. The moment we do a measurement, it collapses to one of the possible state. So suppose I have a state, a polarization state, say alpha kth, where kth denotes a horizontally polarized photon, and beta vv. Ket v is a notation. You just divide the bracket into 2 pieces. Your left hand piece is called bra, right hand piece is called ket. So this ket is denoting a state. So a ket h is denoting a horizontally polarized photon, and ket v is denoting a vertically polarized photon. So now if I do a measurement with horizontal vertical basis, then with mod alpha square probability it will be horizontal, with mod beta square probability it will be vertical. But before measurement it is simultaneously in both. So if we think of a single photon I am sending through this beam splitter, it is both transmitted and reflected. When I measure, it collapses either to the reflected path or to the transmitted path. So this simultaneous existence in both the path or both the states makes a qubit. So an electron is in 0 and 1. The photon is in transmitted as well as the reflected path. So this makes a qubit. So there are many ways you can make a qubit, but for quantum cryptography, we always use optical qubits, because you have to send it from one place to other place, and then photonic realization is best. Now we come to basic ideas of quantum mechanics which can be of use. So for every physical observable, there is an operator, and the operator is Hermitian. Hermitian, why it is Hermitian? To have real eigenvalues. So if we don't go in detail about that, so just we mention that, then there is something called uncertainty principle. So if there are 2 operators and they don't commute, then we cannot measure them simultaneously with arbitrary accuracy. Now I introduce measurement operators. So if I want to measure a state and want to collapse it into ket I, then the corresponding operator is ket I bra I. So then if I have a measurement operator for horizontal polarized state or zero state as M0, so that will be ket 0 bra 0, and M plus will be ket plus bra plus. They don't commute. So that essentially means that Heisenberg uncertainty principle ensures that as they don't commute, I cannot measure them simultaneously. And from this inability, the secrecy of BB84 protocol arises. So if you are not very familiar with these things, you can skip. Then there is an equation which is the main governing equation of quantum mechanics, and now it is even included in class 11. So probably some way or other, sometime we all have read it. H ket xi is equal to E ket xi, where H is the Hamiltonian of a system, and time dependent Schrodinger equation is written in this way. So if I solve, I get that xi t is e to the power minus I h t by h bar xi k xi 0. So what does it mean? Xi 0 is the input state at t is equal to 0. Within the interacting with the system defined by Hamiltonian h, after time t, it will become xi t. So this is nothing but a gate. A gate is something which maps the input state into output state uniquely. So for a particular choice of h and t, every input state xi 0 will map to xi t. Now, since h is Hermitian, I can take u dagger, and you can see that I will become minus I, and h dagger is equal to h being Hermitian. So u is unitary. So all the gates are unitary. Not only that, every gate actually does a computation. So that's true for AND gate, OR gate, NOR gate, NOT gate. So you can see that in NOT gate, you give a function x, it will give you, NOT gate computes a function x, where x is input and x bar is your output. So these are the simple background which will help us to formulate rest of the thing. Then we talk about a simple algebra. So state gate 0, which is my fundamental state, is defined as a simple matrix 1 0, a column matrix, and state gate 1 is defined as 0 1. So then what is my qubit? Qubit is alpha 0 plus beta 1, which will be alpha beta, a column matrix. Now, if I write a plus state which is at 45 degree and 1 by root 2 0 plus 1 by root 2 1, so this is plus, and 135 degree is 1 by root 2 1 minus 1 column matrix, and then I can write the corresponding operators, and I can see that m plus and m0 do not commute. That means I cannot do a measurement in plus minus basis and 0 1 basis. But if you write m0 and m1, you will see that they will commute. So you can simultaneously measure in horizontal and vertical axis. So there is something called tensor product. So here the multiplication happens in this way, that if I have the left hand side matrix A11, I multiply with the entire right hand matrix. Just in this way. So you see that I had a 2 cross 2 matrix and another 2 cross 2 matrix, and now I have a 4 cross 4 matrix. So if I had a column matrix 2 cross 1 and another column matrix 2 cross 1, it would have been 4 cross 1. So this is how the quantum mechanical states increases in size. So if I have to write gate 0 0, or state of a 2 qubit, that will be 1 0 0 0. So a n qubit state will be a column matrix 2 to the power n cross 1, and then the corresponding gate or the circuits which is operating on that will be 2 to the power n cross 2 to the power n. So since the growth is in exponent, with a classical machine, I cannot compute or simulate a quantum system. So to simulate a quantum system, I always need another quantum system. Anyway, so there are simple gates. So I already told you that the 2 qubit system will be 4 cross 1 matrix. So if I need a gate which maps a 2 qubit state to a 2 qubit state, it has to be 4 cross 4. So this is a control NOT gate, which is very famous, and control NOT gate does what? If it is a 0 0, it's like a truth table. 0 0 goes to 0 0, 0 1 goes to 0 1, 1 0 goes to 1 0, and 1 0 goes to 0 1 1, and 1 1 goes to 1 0. That means if the first qubit, which is called control, if it is 1, then the target flips, and if the first qubit is 0, then nothing happens to the target. And now here is a Hadamard gate which maps 0 to plus and 1 to minus, 0 to 1 by root 2 0 plus 1 by root 2 1. So I just wrote a few gates. Now here I define something which does not have a classical analog. So I told you that there are two kinds of communication. One is called teleportation, and teleportation and its varieties like remote state preparation and such thing. So this is, we are explicitly doing the teleportation circuit. So we start with 0 0. So this is Alice and Bob, and if I apply a Hadamard, then first 0 becomes 1 by root 2 0 plus 1 by root 2 1, and that works like a input of control gate. So if the first one is 0, second one is 0, first one is 1, third one becomes second one become 1. So I have a state 0 0 plus 1 1 by root 2. Here I cannot tell that which one is the state of the first qubit, which one is the state of the second qubit. So this is called entangle. So Alice and Bob share an entanglement, and then Bob receives a state alpha kate 0 plus beta kate 1, which he wants to communicate to Bob. But alpha and beta can be, say, mod alpha square plus mod beta square is 1, but you don't know how big is alpha and beta, means how many digits are required to communicate. So you essentially need arbitrary many, infinitely many digits to accurately communicate. But here what we are doing, we are applying this Hadamard followed by C0 circuit in opposite order, C0 followed by Hadamard, and doing a measurement. And the measurement outcomes are sent by classical channel to Bob, and depending upon the measurement outcome, 00, Bob applies 1 identity. If 01, Bob applies X gate, which is a NOT gate, and so on. And in all cases, he received alpha gate 0 plus beta gate 1. The beautiful thing is that this state alpha gate 0 plus beta gate 1 never travel through this channel. And the moment it is received, it is completely lost from here. So alpha beta, either you go 00 or it's 01 or 10. So it's neither like fax. In fax, you have a copy at your end, another copy is created. In a letter, the letter travels through the channel. So this has no classical analog. So as if it disappears from one state and it reappears. So what actually disappears is the information about the state. So there are many things which happens from that, but you can teleport a state to one place to another place only. So you cannot teleport a state from one sender to two receiver. If that was allowed, then it would have mean that you can clone the state. You can make 2 copies of alpha 0 plus beta 1. And if you can clone, then in one copy you can do a measurement on position, another copy you do a measurement on momentum. And Heisenberg uncertainty principle tells you that position and momentum cannot be measured simultaneously. So it implies that cloning is not allowed. Since cloning is not allowed, so I get some other no-go theorems of quantum communication. Since cloning is not allowed, an unknown quantum state cannot be broadcasted. So that leads to no broadcasting. So there are many such no-go theorems which can be followed from here, and they are integral part of quantum communication. So how it is done? It's done with the optics. So here is something called BBO crystal. Here is a palm beam. So this is a nonlinear optical crystal, and it creates an entangled state. And sender applies this kind of operation. So there is a beam splitter followed by a polarizing beam splitter, and here is another polarizing beam splitter. So a beam splitter is something which partially reflect, partially transmit, whereas polarizing beam splitter allows the horizontal light to pass and always reflect the vertical light. So I'll come back to this in context of cryptography, but the message is that, so these tasks are involved in experimentally realized involving simple optics. So here we show that there is a teleportation channel, and somebody from New York went to, say, New Delhi to New York, and his nose and ear has been changed, and he is talking to teleportation hostess like air hostess, and she is telling that because of noise we cannot reach fidelity 1. So that's the problem. So there is a lot of decoherence, and making an exact copy is very difficult. So now we have a preliminary idea of what kind of things may happen in quantum world. So here is Bob, who is asking Alice that you went to Wonderland. Have you ever been to Quantum Land? And Alice says that yes, but you have to take a spacecraft for that. But this is not really a spacecraft. This is a space-time craft, because it's not still ready. So not only you have to travel in space and go from one point to other point, you have to travel in time also to understand what are feasible things in quantum world. So before we reach quantum world, we need to know certain things. So this is just a immigration office in quantum world, and here they will ask you for a green card, answer is P equal to NP, is BQP. These are the complexity classes. So my previous speaker was speaking about certain kind of problems which apparently does not have a quantum algorithm at the moment. So at the moment it is believed that quantum algorithm can be used to solve problems following under BQP complexity classes. So people look for problems which are in NP complexity classes, but if there is a problem which is in NP but not in BQP, so if BQP is a subset of NP, and if we can prove that quantum computer can prove only BQP problem, then post-quantum cryptography survive. So otherwise post-quantum cryptography is a classical cryptography. It's not using quantum resources, but it's based on, it's not even unconditionally secure. It's based on the condition that, on the assumption that quantum computers will be able to solve only the problems in BQP, and further assumption that there are problems in NP which does not belong to BQP. So to understand that, let's understand what is algorithm. So algorithm is a systematic procedure to solve a problem. And what is complexity of an algorithm? So just check that if I have to add a 4-digit number to a 4-digit number, so I write these numbers, and then I add the rightmost digit with the rightmost digit, then the next digit, and so on. So it involves 4 steps. But when I do a 2-digit number multiplied by 2 digit, you see that first I do multiplication twice, then another twice, then adding thrice. So I'm involving 7 steps. So even multiplication of 2-digit number by 2-digit number is more difficult than adding 4-digit number to 4-digit number. So the number of steps is a measure of complexity. If the number of digits increases, how the number of steps increases. So if the problem size increases like n, and number of steps also increases in n square, so then, or n cube, or any polynomial, then I'll call it polynomial time. So even shorter than polynomial, like n to the power half or log n, will belong to this class. So these are the problems which you can solve easily or within reasonable time. So there are problems for which we don't know a solution which works in polynomial time. That does not mean that there is no solution, but we don't know such a solution. So at the moment, the belief is that there are problems which are in NP and which we cannot solve in polynomial time. But with some bounded error, I can solve some of those problems. So classically, they are called BPP, and the corresponding quantum problem class is called BQP. So as far as we know, the solutions, algorithms, quantum algorithms, they all belong to BQP complexity class. So all the post-quantum cryptographic problem which previous speaker discussed and the next speaker will talk, they belong to NP, and it is believed that they are outside BQP, and it is also believed that quantum algorithms will be able to solve only BQP problems. If so, then post-quantum cryptography survive. Otherwise, post-quantum cryptography has the same problem. And if there is a quantum cryptographic solution, why should I go for a classical solution, which is still not unconditional? Anyway, so already previous speaker talk about Grover's algorithm. Just to understand that, what do we mean by complexity classes and algorithms? So here is a teacher who asked that I give you a telephone directory and give you a phone number and ask you to find out the name, because it's normally arranged according to the name. So phone numbers is, if I tell you number, it's a disordered set, it's not a arranged set. So how many searches you need? So as mentioned in the previous lecture, it will be root n in quantum world and n by 2 are of the order of n in the classical world. But a student told that I'll do it in one search. How? He said that I'll call this number and ask his name. But this is not an algorithm. It may work in one go and it may not work in one go. But there is always a possibility that it may work in one go. So it may work. So that's the problem with the classical cryptographic thing. So classically, it depends on complexity of a problem. So suppose factorization is the problem, and I randomly choose a large number and divide, and it may turn out that that's my solution. So there is always a possibility that very fast I may end up getting the answer. So anyway, so to make the problem or make your key more secure or secure for longer time, you have to increase the key size. So here is a table that what should be the bit length if you want to key the secure until the year. So all these things intrinsically involves assumptions that on computational power. So the whole things change in 70s when RSA and Diffie-Hellman appeared, but this complexity based security has many assumptions. So here we mention once again, student did very bad and got F grade in an exam, and a teacher asked that why have you scored so bad, and he said that all the problems were in NP in the exam, and that cannot be done in 3 hours exam. So teacher told that if you don't study, it will always appear in NP. So if we don't investigate properly, a problem may appear in NP and not outside BQP. But a good study, a new approach may find out another quantum algorithm. So far quantum algorithm designing is not a very mature field. So there are only a handful of quantum algorithms, and there are several reasons. We live in classical world. We don't have a quantum computer where we can play and by trial and error generate new algorithms. But Peter Short changed the notion of cryptography. Although the 1984 the quantum cryptography paper appeared, but classical cryptography was not in crisis, so people were not that much interested in quantum cryptography. But in 1994, Peter Short came up with an algorithm which can do factorization of Suppose you multiply two large primes and then you ask to factorize, and so source algorithm can do that, and but it requires a very large register, and it's very difficult to make such a large registers at the moment. So this was something where which changed the whole scenario of quantum cryptography. And there is a good thing that now we have accessible quantum computers, and we can factorize very large numbers. But what stops us from making a very large quantum computer? So decoherence is the villain. So to understand decoherence, here we show a cartoon. So when a quantum system is taught in my school or college, I was taught that there is a particle in a box, so there is particle and box and nothing else. But in reality, apart from particle and box, everything is interacting. So there are atmosphere, environment, so we can think about everything else as environment. So when there is a nice experiment is happening in some Caltech or MIT, I'm also part of the entire environment. So environment and system interact, and the total Hamiltonian has three parts: system Hamiltonian, environment Hamiltonian, and interaction Hamiltonian. And it becomes an open system. So, and that unwanted interaction leads to unwanted changes in the state. So I told you that alpha ket0 plus beta ket1 may collapse to ket0 and ket1, but it may be undesired collapse because of its interaction with the environment. So anyway, here is an interview, and the student was asked that what is your contribution to quantum computing, and the student said that I was part of environment in every successful experiment. Now, we already mentioned that it collapses. So now I show you something. So here is a beam splitter, and a single photon is coming. So if you can see in my hand, so this is the ID quantic product. This is the simplest quantum cryptographic product which is in the market, and I thought that I'll give a demo, but it may be time consuming. So it just looks like this. This is, you can connect in USB, and once you connect in, there is a port, and so what is inside? There is a beam splitter, and there is a semiconductor laser and a beam splitter followed by two detectors. So this is like this. So when the single photon, this detector clicks, means it collapses here, I note it as 0. When this detector clicks, I note it as 1. But it's a quantum mechanically, it's completely random. And this randomness can be tested, and you can check that it's really collapses randomly using the IBM quantum computer also. So in IBM quantum computer, I apply a Hadamard gate and check that it collapses to 0 or 1 randomly. But so this is the ID quantic product, and then we check. We apply Dieharder test, NIST test, etc. to check that it's really random. Anyway, so what is the use? So of course, random number has multiple uses. So classically, you cannot have truly random number, because if you toss a coin, if you know the force, you know the air drag, etc., you will be able to predict that what will be the outcome. So quantum mechanically, it's intrinsically random. This randomness comes from the intrinsic randomness in the theory. And ultimately, a key has to be random. So generation of random number is not sufficient. I have to distribute it from one place to other place. And now I talk about something called interferometer. So interferometers are easy to understand, and we know from school that condition for interference is to create two coherent sources. So if I have a beam splitter, one reflected ray and transmitted ray are created from one source, so they are always coherent, but they never meet. So I put two mirrors, and the mirrors send them back, and then this detector they meet. It's called Michelson interferometer. But there are other ways they can meet. So I can put a mirror in 45 degree, another mirror in 45 degree, and ask them to meet here with another beam splitter. Then it's called Mach-Zehnder interferometer. And when they are turned back, then it's called Sagnac interferometer. So role of this M1 and M2 in Mach-Zehnder is simply to send the output of the beam splitter to the input of the next beam splitter. So realizing this kind of setup in IBM quantum computer is easy. You just need to apply two Hadamard gates, and in fiber also it's very easy. because in fiber you don't need that mirror, you just make a loop and you can have. And the beam splitter is just like optical coupler. So since many people in C dot works with the couplers and fiber, so I thought that I'll show this. Now this gives you a very preliminary idea of quantum mechanics. Suppose there is a photon 0 and it's 1 by root 2 0 plus 1 by root 2. That's my claim when I am claiming the random number generator. But if it was like there are balls and the ball either goes here or goes here with half the probability, then also it should have been same. But now I continue with the Mach-Zehnder interferometer and I see that in one of the beams detector it's clicked 100%, in the other detector it never clicked. So here constructive interference happens, here destructive interference happens. So this is manifestation of wave nature and proves that actually quantum state was in superposition. So if it was ball kind of setup, that 50 ball go out of 100 ball, 50 goes here, 50 goes here, then out of those 50, the lower 50, 25 would have come here, out of the upper 50, 25 would have come here, and the 50 balls would have been clicked in the red detector, 50 on the black detector. So quantum mechanics is valid, and this is what we want to use for quantum key distribution. So these are Mach-Zehnder interferometer and Michelson interferometer. So the D is Michelson, A and B are Mach-Zehnder, and C is also Mach-Zehnder. So here we show something, that there is a source beam splitter Mach-Zehnder interferometer, and if this absorber or bomb was not there, then this detector D2 would have been clicked. Now what is the role of this bomb? So this is called Elitzner-Wedman bomb testing. So if I send a photon, then if it passes through this is like a detector, it clicks or blasts, or it's an inactive bomb, then it passes through. But now if I send, putting a detector in one path means you are knowing the which path information or particle nature. And the moment you know this path, if it is not here, it must be here. So you don't need to put another detector here. So then the wave nature is lost. So the moment you know it is in 0 or 1, in which path it is, it's no more in superposition state. So out of 100 photon, 50 goes from here, 50 goes from the top, and out of those tops, since wave nature is no more there, so 25 will go to D2 and 25 will go to D1. So these 21 is manifesting the cases where there is an absorber or a bomb here. The presence of the detector is detected 25% of the times without sending any photon. So this is counterintuitive. I send no photon, but I still can detect. Now how it can be used for generation of quantum key? Now here is a Mach-Zehnder interferometer. Left hand side is with Alice, right hand side is with Bob. And Alice and Bob randomly put absorbers. So 4 cases may happen. None of them put absorber, then D2 clicks. Both of them put absorber, no light passes, nothing clicks. One of them put absorber, D1 clicks sometime. If D1 clicks, Alice knows whether she has put it or not. So if she has not put, then it must be Bob. And Bob knows whether he has put it or not. So if he has not put, then it is Alice. And they may pre-decided that if Alice has put it, then it is 0. If Bob has put it, it is 1. So they have a symmetric key and using Mach-Zehnder interferometer. So this is Goldenberg-Wedman protocol. So here we use the orthogonal state. So it's like the packet which goes from the top is called Kt, and the packet which goes from the down path is called B. So Kt reaches and wait here, and then Kb starts. So never the states are like A plus B by root 2 is 0 or Kt minus Kb by root 2 is 1. They are orthogonal, but since A plus B and A minus B are not simultaneously present in the state, if Bob cannot do a measurement in this basis. Anyway, now to give an introduction to what is done in C dot. So Dr. Atul Gupta will speak after me and talk about this kind of encoding. So this is not, there are many different kind of encoding that can happen. So here we show something that I have a laser and it goes through a beam splitter, and so this is a beam splitter followed by a mirror and then another beam splitter. So this is nothing but a Mach-Zehnder interferometer. But in Mach-Zehnder interferometer, this black pulse can follow 2 paths. Either it can go from the top path, which is longer, or it can go from the short path. So if it goes from the short path, naturally the loss is less because it has traveled less distance, and also here is a loss we have shown in the red. So because of the loss, the red path has become smaller photon, and it's reaching also after some time because this is taking longer time. So I have the red one is the one which has traveled from the top, and there I have encoding a phage. Now here is again the similar module, and what happens to the detector here, or so more detail in the next talk, would depend on the phase difference between the two consecutive pulses. So whether they are in phase or they are out of phase, it will depending upon that the detectors will be clicked, and this is called phage encoding. So even that uses Mach-Zehnder interferometer, and the DPS QKD, which has been implemented in C dot, uses this kind of encoding. So now we come to the simplest protocol, the first one which was introduced, BB84. So Alice prepares a random sequence of 0, 45 degree, 90 degree, and minus 45 degree polarized photon. So this we can call as 0 degree is 0, 90 degree is 1, 45 degree is plus, and minus 45 degree is minus. So Bob measures those bits in randomly in plus and rectangular basis. So plus basis is like a horizontal vertical basis 0, 90 degree, and rectangular is 45 degree, 135 degree. So if you measure a 0 degree in plus minus basis, it will be 0. If you measure a 45 degree, 45 is like 1 by root 2 0 plus 1 by root 2 1. So with half probability it will be 0, half probability it will be 1. So the trick is there, that, and then they compare that which cases their basis matches. So only those data are kept. So if the basis matches, so it becomes half of the cases their basis will match. So if they have measured a 0 state is measured in 0 1 basis, or a plus state is measured in plus minus basis, it must give plus. But in between, if there was a Eve and Eve did some measurement, then that will lead to incorrect result. So for example, so they will compare half of the remaining to check that Eve is there or not. So you assume that Alice has sent a 45 degree polarized photon, and Eve has measured in 0 1 basis, and Eve got it horizontal. So Eve has sent a horizontal, but horizontal is also 45 degree plus minus 45 degree, or plus minus by root 2. So with half probability, Bob will find it correct, but with half probability it will be incorrect. So whole point is, half of the time Eve will choose incorrect basis, and so then he has changed the result, she has changed the result, and out of those, half will lead to a traceable, detectable trace. So 25% of the time Eve will be detected. So this is what makes the difference between Alice and Bob. So we are in a process of, this is the difference between Eve and Bob. So Eve will leave a detectable trace because he does not know in which basis the qubits are prepared and in which basis Bob is going to perform a measurement that's random. So Eve will perform, if we'll choose half of the time incorrect basis, and that will lead to detectable trace. So classically, no eavesdropping attack leaves trace, but here we have trace and we are just generating key. So if such a trace is discovered, we don't continue. So this is a small device which is in our lab. So this side is Alice. So these are, and here is a polarizer. So this side is Alice, here is a source, and here is a polarizer, and then Eve has similar apparatus similar to Bob and Alice. So this is intercept and resend attack, as if Eve measures and then recreates the state and send it to Bob, but it leaves a detectable trace. So we just keep only those cases when the basis matches. So without elaborating on this, so this is what the space stations do. So suppose there is a space station one in China and the other one is in Austria. And now when the satellite is above China, it generates a key 1 following BB84 protocol shown above or described earlier. And say when it is above Austria, it generates a key 2. And then it discloses key 1 XOR key 2. Since this guy in Austria knows the key 2, so he XORs once again. So key 2 XOR key 2 opens up, and he also has a copy of key 1. And already China has a copy of key 1. So they have the same key, and then the satellite has no role, and they can communicate using that key. So not only China has done that, there are many countries which are trying, including we are also trying, and there are several groups including PRL and RRI who are more interested in doing this kind of things, and SAC, and also DRDOs are interested in satellite-based quantum communication, and probably very soon we'll also have stations. But these orbits are normally low Earth orbit, and the communications happen from low Earth, and it is easier that we perform the communication from top down, satellite to Earth, because satellites are small, their telescopes are also small, and the atmosphere is only 8-9 kilometers, and after that, if there is a fluctuations, the deviation will be very large, and it will be very difficult detecting from the satellite. But if the deviations happens in 8 kilometers, separation will not be very high, and also you can launch larger telescope in Earth. So top-down approach is easier, but of course people are trying other approaches as well. So I skip telling you about B92 protocol, and I draw your attention to the point that QKD itself is not an application. The application is when you are doing communication. Like I show you that and before doing QKD, you have to do authentication. So that cannot be done completely quantum mechanically. So there must be, although we talk about public key cryptography and all such things, so there must be some essential secret initially shared, and it may be essentially an entanglement which is pre-shared, but something must be pre-shared which will help Alice and Bob to authenticate that Alice is really talking to Bob, or Bob is really talking to Alice. So authentication is a very crucial part. So QKD stands on top of that. Then there is privacy amplification, and all on top of everything there are applications like secure communication. So what are the challenges? So now we show a cartoon that here is a QKD shop in Delhi at T2021 now, and what it can sell. It can sell SNSPD, which is single photon superconducting nanowire single photon diodes, that are the best single photon detectors. So single photon detectors quality is not very good. It can sell Quantis, which I just show you, random number generator, quantum random number generator. It can show Clavis 3, which I show you in the flashlights, APD, payloads for going in satellite, BBO crystals for creating entanglement, weak coherent pulse sources. So you have a laser and you apply attenuator and make approximate single photon source, but it cannot sell you polarization preserving photon number resolving detector. So quantum mechanics does not stop me, but it's not there. It cannot sell you quantum repeater. It cannot sell you single photon detectors, on demand single photon sources. So if tomorrow such things are available, so in, I don't know what is delta, but sometime later, and then we'll really be in quantum world and we'll be able to do many things, but still we will not be able to do perfect cloning, which is not allowed. Quantum broadcasting, I already mentioned why you cannot do that, because that will be violation of Heisenberg uncertainty principle. Accurate measurement on 2 or more MUBs, so this will still not be allowed in the quantum world. So as you see that B92, BB84, counterfactual, differential phase shift, cow, there are so many options for doing quantum cryptography. So which one is the best QKD? So if you want to do it for short distances, continuous variable QKD is a better bet. They can be implemented with the present technology, does not require single photon sources, but the homodyne measurement involved is pretty difficult. Now, the best all around the best thing is the device independent QKD. But device independent QKD means that even if you have an unconditional security, but it ultimately has to be achieved through the devices, and the devices may be inaccurate. So how can you make device independent QKD? Of course, there are proposals, but that require 100% efficient detectors, which you cannot make. So what is practical is to make measurement device independent QKD. So at the moment, measurement device independent QKD are very good, and a very interesting idea is twin field QKD. So measurement device independent twin field QKD in CDOT's internal seminar circuits we have discussed earlier. So we don't have time to discuss those things, but I just, for interested participants, you can explore the MDI QKD and TF QKD. And for short distance, it is always beneficial, or metropolitan network, to look for CB QKD. But as far as the security bars are known, they are best known for BB84 protocol. So anyway, so security is not restricted to communication only. So they are extended to other facets of computing also, or cryptography goes for quantum voting, So we have a project in the US project and we work on quantum voting. So recently we worked extensively on quantum veto. So what kind of solution can help the Security Council of UN to use quantum resources for doing anonymous veto. So here is a simple protocol that you start with a qubit state. So instead of 2 level, there are k level states and entangled states, and one particle is kept with the tally map who will count the vote, and the other one is sent to the voter, and the first voter, if it is a yes vote, he shifts it by 1 unit k plus 1 and send it to next and next, and then finally you do a measurement, and from the measurement I'll know that how many yes vote and how many no vote, but it will collapse to one of the possibilities. Suppose this is the starting state and there is only one yes vote, so then it will be 1 0 2 1 and 0 2. So if I do a measurement, I'll either get 1 0 2 1 or 0 2, and from that I'll know that how many yes vote has happened. So there are other things like auction, lottery, and such things also deserve. So casinos can already use quantum random number generator. So there are many connected cryptographic problems where quantum mechanics can play a role. Now it's not expected that, suppose bank is providing you a security, and that it's not expected that everybody will have a quantum computer at home and they will be able to generate qubit and things like that. So can it be extended to classical user? So this is a BB84 kind of thing, semi-quantum version, where Alice or the bank has a quantum resources and it generates 0 1 plus minus states randomly and send it to Bob. Bob randomly measures it in 0 1 basis, which is not superposition, so he is a classical user, or just reflect it. Then 4 things can happen. N by 4 cases, Alice send in Z basis and Bob measures. Alice sends in Z basis, Bob reflect. So reflected cases, they can find out whether in between there is a eavesdropping or not, because Alice will perform measurement in the same basis in which she has prepared. So she will be able to trace eavesdropping, and in these cases the key will be generated. So this will be, key generation rate will be smaller than BB84, but you can extend it to a classical user. Now this leads to a problem called delegate quantum computing, blind quantum computing. Now IBM and all such people are generating cloud-based services. So I have a laptop, I have a mobile phone, I'm buying a service. How do I know that they're really doing quantum computing? How do I keep them blind about my work? That if I want to do factorization, if they know the factors, then it becomes public. So can I keep them blind and still do the job? If I have a completely classical, so I'm actually delegating the job to IBM, cloud-based quantum computer. So this kind of secure communication, you can keep it blind and delegate the job, provided either you are able to generate single qubits or you can do quantum measurement. But if you just a classical laptop or classical computer, you cannot make it blind and delegate the job. So I'll skip this thing. So this is where we stand now. So we use QRNG to select winners. So this is a casino, and say casino in Macau. Somebody can, Sikkim State Lottery can use quantum random number generator like quantities which I have shown you. And so there are tasks which can be done with quantum resources, and the resources which are very relevant for quantum communication. UNO can ensure it's, because this is a small number of voters, can do it for quantum veto. We are strongest democracy as we elect MPs by using quantum voting, but that's a futuristic task because handling large number of voters is very difficult at the moment. We are corruption free as we conduct all auctions using quantum seal bit auction. So this may happen in future, but the top one task that UNO can still conduct quantum veto. So that much, because there are only five voters which has veto power. So Atulji, can I take 5 more minutes? Can I speak for 5 more minutes?
Yes, sir. Yes, sir. Yes, sir. You can conclude in next 5 minutes. So we have a question also.
Okay. So 5 minutes I'll conclude. So as I mentioned that we actually prepare quantum communication quantum cryptography is expected to be unconditionally secure, but it's prepared with the devices, and the devices are not perfect. So unless I am doing a device independent quantum cryptography, so there is always a possibility that I use imperfection of the devices and exploit the imperfection of the devices. So here are things. LD, there are 4 light dots, 1, 2, 3, 4, and one in front of that there are different kind of polarizer. One is horizontal, one is vertical. This is diagonal, this is anti-diagonal, this is horizontal, vertical, and we mix those things. Now here is a circulator. Circulator is an optics which allows the light which is coming from path 1, it goes to path 2. If it comes from path 2, it goes to path 3. So this. So if it comes from path 3, it goes in path 1. So now it's simple application of Melrose law. So if gives a strong pulse through this and sends it inside, then this will, since this is vertically polarized, the vertical polarizer allow it to go completely, others will allow it cos square theta. So cos vertical is perpendicular to horizontal, so nothing will come here and the wavelength remain unchanged. Here the temperature will increase and the wavelength will change maximum. Here the wavelength will change minimum, moderate. So one will become lambda 1, one will become lambda 2, other one will become lambda 3. So I can measure the wavelength and then decide that in one case I do a measure. I already know that it is lambda 1, then it is horizontal. If it is lambda 3, it is vertical. And if it is lambda 2, I apply a wave plate to make it horizontal vertical. So just rotate by 45 degree and then it's a polarizing beam splitter. So horizontal will pass. So diagonal has now become horizontal. We have rotated 45 degree in the clockwise direction, and anti-diagonal has become vertical, say, and so that's reflected, and this is after. So we know, so not only the photon has to be same in, they have to be same in all degrees of freedom. So their wavelength must be same, any degree of freedom must be same. Now how to save from this attack? I have to put another circulator inside the Alice's end. So this is a simple attack, but this kind of attack people have done. And what I was telling you again and again, that Sivp cryptography is a good candidate for short distances. So it shows that how key generation rate changes with the channel loss or the distance. So initially you can see that Sivp MDI-QKD is performing better than DB MDI-QKD. So for short distance metropolitan network, Sivp is a good bet. There are 3 kind of attacks. Individual attack, that each qubit is attacked individually and you cannot access, if cannot access collectively the joint attacks on the qubits of no joint unitary operation as well as joint measurement is possible. In collective attack, joint measurement is possible, but joint unitary operation is not possible. And here both are possible. So coherent attacks are most powerful attack. And when I prove something, I have to show that my protocol is secure against coherent attack. But when I want to attack something, the technology which is available commercially or in the labs are only capable of doing individual attack at the moment. There are other attacks, like we can use the detector efficiency mismatch of the. So detectors works in this way. The detectors we are talking about, that there are detectors along the reflected path and the transmitted path, and they detect equally but with equal efficiency. But if I just change the time, so at this time their efficiency was equal, but at this time eta 1 has more efficiency than eta 0, and here eta 0 has more efficiency. So by shifting the time of arrival of the pulse, if can decide that which detector will click. So similarly, beam splitter has different kind of. So a 50-50 beam splitter is supposed to reflect 50%, transmit 50%, but that happens in 1550 nanometer. If you just change wavelength, then it can be completely reflecting, completely transmitting, and changing wavelength, if can decide that which side it will go. So which kind of measurement will work. So these are different kind of attacks possible. So here is something called Trojan horse attack, which is very common attack. And here I have a laser and a polarizing beam splitter, or just a beam splitter. It goes through the modulated, and through circulator is to go to Alice's port, and on return circulator will send it here. So the first beam become reference beam, and I chase the phase difference between these two. So if the Alice's port has beam splitter, commutator, variable attenuator, and all these things, say connectors, phase modulator, so from each of them the light returns, some part of light reflect and some phase information is received here, and we can get some information. So what is the rule for avoiding Trojan horse attack? Once again, you give a circulator to Alice. So this is the almost the last. So here Bob is telling Alice that I don't trust you. So Alice asked, why? Because you reflect light. Eve can. So Alice says that that's why you can see me, but Eve can also see you. So then Alice says that, then give me a circulator. So circulator is the optics which can avoid this attack. And then here is the last one, that Alice is telling Bob that don't send me personal message because Papa or someone else may eavesdrop. So, and Bob is saying don't be afraid. So this channel is quantum secure. So when quantum secure channel will appear, the bank situation will be like this, that everybody will close the bank, close accounts in classical bank and open in quantum bank, and we are going through a continuous journey to that, and finally we want to go to a QKD shop where all these things will be available, that which is quantum mechanically allowed but not available at the moment. So towards that, India has many initiatives. So there are two Quest problem program. One, the bigger program is of DST ICPS, and many of us have projects from that. So many of our activities are supported by Quest. So involved institutes on quantum, especially on quantum cryptography, are PRL and RRI are on satellite-based quantum cryptography. ISAR Mohali mostly done continuous variable quantum cryptography. We do theoretical part, but we are trying to generate experimentally quantum random number generator also. PPISR does theory. HRI is more on quantum communication, not on cryptography, teleportation, and other Novo theorems and such theoretical aspects of quantum communication. IIT Delhi, there are two groups, experimental group, who are trying to make entangled states. IIT Jodhpur is also trying to make entangled states. In IIT Madras, electrical engineering department has a group, and they tried to make differential phase shift quantum cryptography, and from a project of Principal Scientific Advisor's Office, and that led to a company called QNew Lab, and QNew Lab is now claiming that they have a DPS quantum cryptographic solution or fast commercial quantum cryptographic solution in India, indigenous commercial solution. So there is another big thing to happen is National Mission on Quantum Technology and Application. DRDO has also created a national map and established a young scientist lab called DYSL-QT. Anurag is now closed, but KR is interested in post-quantum cryptography. SAG is on realization of certification. JCB is an end user. DIAT is a university kind of setup, and now DYSL-QT is located. So there are many different labs which are interested, and Real Defense is also interested. Even there is a training school called Military College of Telecommunication Engineering, MCT. They are also interested in quantum cryptography kind of labs, quantum communications for signal people. So, and of course, I'm not elaborating on the activities of CDOT because CDOT people will elaborate on that. So I stop here, and with a final note that quantum phenomena do not occur in Hilbert space, they occur in laboratory. So more experimental realizations are needed, and one such nice step is by CDOT, which we'll listen. So there are many facets, but we don't go in that. Means I'll stop here, and if some simple, quick questions we can take.
Thank you, sir, for making us delve into the captivating dimension of quantum mechanics and its applications in ensuring foolproof security in critical communication scenarios. Sir, we have a question. Sir, as regards the detectability of Eves, if we assume that an Eve can be used for denial of service attack by constantly attacking in between an ongoing session, then what is the breakthrough to manage such conditions? The question has been posed by Mr. Swarnim Agrawal from CDOT.
So it depends on specific implementations. Means that what is the means to what extent denial of service attack can be done. Means there is no one go answer for all kind of implementation. So for example, it is believed that if you have a fiber based thing and your enemy country cannot come and cut your fiber, but if you are a satellite, you are doing it based on satellite, then destroying satellite is very easy. So even when we plan the satellites or ground station, this topology is seen. Means like if you have network of 5 satellites, even if one satellite is dropped, then 4 satellites can survive or not. But if somebody send a missile and destroy your satellite, so your service will be denied. If somebody can cut your these fibers have to be dark, and if somebody can cut your dark fiber, then service will be denied. So that kind of brute force denial of service attack cannot be stopped. So only thing protection is on your network, that if a particular network is cut, then whether you are an alternative path or not, and the much of the topology depends on that, and kind of attacker you are expecting, that also depends on where the thing is located. But physically, if somebody destroys your network, you can really give denial of service. Means that cannot be stopped by. Only option is you can keep some alternate paths.
Thank you, sir, for responding to our queries. So due to paucity of time, we'll not be able to take more questions. Sir, if there are any more questions, we'll mail them to you separately. Thank you, sir. Our next speaker is Sriyatul Kumar Gupta, Head Optical Technologies, CDOT. Sriyatul Gupta has more than 29 years of experience in the design and development of optical communication-based products. He has worked on design of synchronous digital hierarchy, SDH-based systems, fiber access systems, optical amplifiers, gigabit passive optical network GPON, dense wavelength division multiplexing, DWDM equipment, and quantum key distribution. He holds BE in Electronics and Communication from Delhi College of Engineering, Delhi, and MTech in Optoelectronics and Optical Communication from IIT Delhi. Sir, may I request you to share with us CDOT's endeavors in the area of quantum communication?
Good afternoon, everybody. So this presentation will cover the activities related to quantum key distribution at CDOT. So this is what I propose to cover. There will be introduction, and then there will be a brief overview of what we have already listened in detail about classical cryptography and its limitation. After that, there will be quantum key distribution and its applications, and the quantum key distribution activity at CDOT. What are our achievements in this area so far? And finally, we'll summarize. So before starting about quantum key distribution, I think it is important to understand that there is a lot of growth in the digital data traffic. So this particular slide, the data is taken from a Cisco report, and can be seen that in 5 years that it's expected that number of internet users in India, they will more than double. The number of devices and connections per capita, this will also register a substantial increase. And the average data consumption per capita per month is going to witness a huge growth. So there is a lot more traffic which is flowing on the networks, and accordingly, the security also becomes paramount. So there is a lot of dependency on the data now. There is a digitization tsunami all around the world. Our daily lives and businesses are increasingly getting dependent on data. Consequently, there is more concern as far as vulnerability is concerned of the malicious use. Most important thing is that it is very easy to store the data and decrypt it later. So those type of attacks are also getting more frequent. The amount of loss due to uncompromised data security can be paramount. And in fact, there is a IMF statement from head of IMF into 2018, which says that the average potential losses could reach half of banks' net income in extreme cyber attacks. So lot is at stake. Now, I would just like to draw your attention to the fact that there is a tremendous cost which is associated with any breach in data security. So one of the reports from IBM Security, it says that the average total cost of a data breach, so single data breach, the average total cost is of the order of $3 million. So that's for a single data breach. And there is an increase in the average total cost of data breach. If we see year-on-year basis, there is a slight increase, although we can see a slight dip in 2020. But the overall trend is that there is an increase in last 6-7 years. And another thing is that there is a phenomenal increase in the malicious attacks since the onset of COVID-19. So that is also a documented fact. So all these things put together actually ponder us that we should think about data security in more detail, with more clarity and with more detail. So this is something we have already seen. Just a brief recap that how do we secure the communication network? We encrypt the message, and encryption requires a key. If we are using a symmetric key cryptography, then the decryption process will also require the same key. So the message, plain message, will get converted into a ciphertext, and ciphertext is something which is garbage for any unintended user, unless they have access to the key. And finally, that ciphertext is converted back to the plain message by the decryptor using the same key. So it is very important that the key should not get into the hands of any adversary, because if the key is exposed, key is compromised, then there is no point in doing any encryption or decryption. So this is a brief about cryptography, the symmetric key cryptography, which basically uses same secret key on both sides. So key has to be somehow kept secure. It should not get into the hands of an adversary. The examples are advanced encryption system and so on, and it uses typically smaller key lengths like 128 to 56 bits. If we talk about asymmetric or public key cryptography, then it uses different keys. So one is public key for encryption typically, and a mathematically related private key for decryption. So the public key is distributed, and anyone who wants to send a message encrypts the message with public key, and the decryption or decryption process can only happen with the private key. So it uses much more larger key lengths, and examples we have already seen in earlier is that RSA and Feynman. So what is the problem with the present cryptography? Why should we talk about alternate methods? Is that one of the foremost problem is the intrusions remain undetectable. We heard from Professor Anirban Patak earlier that any eavesdropping in quantum world can be detected, but that's not the case with the present cryptography, which is in use now. So intrusions will remain undetectable. Security is based on belief that nobody can factorize a very large integer and or solve any complex mathematical problem, and it is not unconditional. So somebody can have an algorithm and can break that present cryptography foundation on which present cryptography is based. And with the advent of quantum computers, and we heard about the Shor's algorithm and Grover's algorithm, security stands compromised. Brute force attacks on cryptographic keys are easy due to low frequency, and the keys are getting updated at a comparatively low frequency. So brute force attack, if computational power is high, brute force attack like the Grover's algorithm, which can run on quantum computers, that can probably break the cryptographic keys as well. And asymmetric cryptographies are 2 to 3 times slower than the equivalent symmetric cryptographic algorithm. So these are some of the challenges which are there with the present cryptography. So how do we resolve it? Resolution comes from quantum mechanics, which is formulated around 100 years back, and it's now in a position that we can use it practically in practical applications. And it has certain features which can actually revolutionize and things which we currently do in a different way. Quantum mechanics, because of quantum mechanics and advancement in quantum computing, it is possible to break the key. There was a claim by Google of quantum supremacy, means that Google claimed that they have done a task which a classical computer will probably take more than 10,000 years. They are able to do it in a very small time on a quantum computer. And that happened in October 2019. So this is a very important milestone because it shows that the threat is actually real. So the compromise, if the key gets compromised, which is certainly possible if quantum computers come into the picture, then there is no longer any security. We can fight quantum with quantum, and we can use quantum key distribution, another aspect of quantum mechanics, to generate keys which can mathematically be proved to be secure. The security is not based on any assumption or belief or about the computational power at the hands of an eavesdropper. So another important aspect, there are plenty of tools which are available at a very low cost, which can be used to tap optical fibers and retrieve the data which is being carried without anybody getting any idea about that. So once we have the data, and if key is there or if key is extracted even at a later date, then the security of the data transmission is lost. This is important. This is what is known as Moscow's inequality. This is from a mathematician from Canada who formulated a very simple equation which says that, which tells us that when should we actually start worrying about quantum computers or threat from the quantum computers. So it says that if D is the time it takes to keep our data secure, and T is the time it takes our system to transition from classical to post-quantum, then, and if QC is the time that it takes quantum processors to reach a scale where they can breach the existing protocol, then we should actually worry when D plus T is, when D plus T actually becomes greater than QC. And it is believed that the Moscow's inequality has been breached in 2017 itself. So, this is something which has been concluded by experts. So that means there is a real threat from the quantum computers. So importance of QKT we have already heard in greater detail. We have talked about the National Mission on Quantum Technologies also. And one of the important aspects that I would like to bring is that ITUT has also started working on QKT standardization. There are already 5 recommendations which are in place, and more are expected. And this is a recent development. It's not long back. The first recommendation came in late 2019. And there is a substantial market which is predicted for quantum cryptography with a good CAGR. And the use cases are in banking and financial services industry, government, defense, healthcare, IT, and communications. So these are the standards. You can see the first one came in October 2019, around 2 years back. And after that, so basically ITU is taking a holistic view. It is talking about the functional requirement, architecture, key management, control and management. And the objective is to actually make a standard compliant. It is good for the operators. It is good for those who are deploying the QKT solution that there is a standard from ITUT. So very briefly about the method through which Professor Patak already talked about continuous variable QKT. Then there are discrete variable QKT, which encodes the information in the phase, polarization, or time bin of single photons. And there is a subset of distributed variable QKT, which is distributed phase reference. And that encodes the information in time or phase of weak coherent pulses. This is what is most common implementation. CDOT solution is also based on distributed phase reference. And as far as architecture of protocols is concerned, it can be prepared and measured, something like BB84 that Professor Patak described in the earlier in his talk. And measurement assisted is something like measurement device independent QKT. Again, he covered that in his talk earlier. And then there are entanglement based. So entanglement means that the transmitter generates an entangled pair and which is sent to 2 parties, and they receive the quantum state and decipher the key out of it. So these are broadly the QKT protocols. This is how QKT gets integrated with the actual system. So QKT modules are these are commonly known as Alice and Bob. What they do is that they deliver the key to the application, which is an encryptor typically, and on the other side a decryptor. And this interface is standardized. This is the interface which is standardized. So any encryptor can be from one vendor, the QKD can be from a different vendor, and still fetch the key. And these keys are used to carry out the encryption, decryption. There is a classical channel and quantum channel between the Alice and Bob, between the QKD modules, and any eavesdropping on quantum channel will get detected. So that's the whole purpose of deploying QKD. Eavesdropping should get detected. Classical channel eavesdropping won't yield any information about the key. So the key is not compromised if somebody eavesdrop on the classical channel. So that's the thing QKD provides. Obviously, the real network is far more, it's not point to point. So a real network will have a lot more nodes. It will be in different topologies, whether it is ring, mesh, linear, or star. So to accommodate that, ITU is coming up with a QKD network. It's QKD network. Multiple QKD links will be connected through quantum relays or optical switches and splitters, so that one Alice can cater to multiple Bobs or vice versa. And a complex topology can be built of the QKD network as well. Finally, if because QKD will support to a certain distance, a fiber-based QKD, after that the key has to be taken, then there is something called key relay. Key relay will come into picture, and the key will be passed at the two ends. In between, there will be key relays in the QKD network, or there can be an option where the key is passed to every hop, and then the application entity takes care of it, or there can be a mix of the two scenarios. So there can be key relay as well as passing of the key. One can see that the key which are passed to the application entity, even after relay, they are identical. So there is a key K1 here, and the identical key K1 is present on the other side. Finally, what we are doing at CDOT, we are doing product-oriented R&D. We have done the complete hardware and software design in-house, including the key distillation engine, which we have implemented in FPGA. So that forms the backbone of our product. We have signed a memorandum of understanding with Physical Research Laboratory. Professor Patak mentioned about their effort to build a satellite-based QKD. So what we plan to do is to integrate our fiber-based QKD with PRL's free space or satellite-based QKD. We have signed an MOU with the IDRBT because we want to explore the use case of QKD in the banking and financial services industry. And CDOT intends to play a key role in realization of goals and objectives set under quantum communication vertical. Our executive director mentioned in his introductory remarks that we are already being considered as a technology innovation hub for the quantum communication vertical under the NMQTA. So as I mentioned earlier, we have completed the design. The product is ready. It was launched on 9th by Security Telecom. And it gives good performance in terms of secure key rate, which is better than 1 kbps, and a quantum bit error rate, which is better than 5%. We have tested it with more than 100 kilometers of actual fiber. We have integrated it with our CDOT's router as well as PQC equipment as per the ETSI standard to have a complete solution. We have filed 2 patents. One more patent is in the pipeline, and we have created a setup for simulating the photon number splitting attack because practical QKD implementation uses weak coherent pulses. So photon number splitting attack is one such attack which should get detected, and therefore we have simulated a setup, actual hardware setup for simulating that. So with this, we have actually we have all the solutions. We are already these are the solutions which are already there with CDOT, or they are in the advanced stage of development, whether it is in optical access or in optical core, whether it is dense wavelength division multiplexing or packet optical transport platform, or front haul 4G, 5G, front haul, mid haul, 4G, 5G RAN and core. So these are all under development, or they have already been completed and are under POC. Encryptors as well as switches and routers, and with QKD and PQC, which my colleague will talk in the next session, all this will be quantum secured. So this will be basically an end-to-end telecom solution from CDOT, which will be quantum secured. So summary, basically to summarize, the security of data being transported is under threat by rapid advancements in quantum computing. We saw that lot of data which is being transported needs to be kept secure for a number of years. It doesn't really matter whether it gets decrypted today, but it can probably be stored very easily and decrypted later on, and still it will compromise the security. We saw that Moscow's inequality has been believed to be already breached in 2017. Another issue is the large-scale deployment of 5G networks will further aggravate the security aspect, because a lot of devices will get connected to the network. Industry automation will take place, so everything will require foolproof security. QKD addresses the security issues and provide information theoretic security. It doesn't depend on the computational power at the hands of an eavesdropper. And CDOT is actively pursuing QKD development, tends to play a key role under national mission on quantum technologies and application. With a vast range of indigenously developed communication products and solutions, CDOT is eminently poised as a trusted source of quantum secure end-to-end communication infrastructure. With this, I would like to conclude. Thank you.
Thank you, sir, for giving us insights into CDOT's forays into the world of quantum communication. Our next speaker is Shri Prashant Chugh, who is currently working as a group leader in CDOT. Shri Prashant has more than 25 years of work experience in telecommunications research and development. He is currently leading the development of post-quantum cryptography-based encryption products in CDOT. Shri Prashant is a senior member of IEEE and is currently the chair of IEEE Communication Society, Delhi chapter. He holds a BE in Electronics and Communications from Netaji Subhash University of Technology, formerly NSIT, and MTech in Computer Technology from IIT Delhi. He also holds a certification in cryptography by Stanford University and a certification in deep learning specialization earned through Coursera. Sir, may I request you to share with us the details of CDOT's R&D initiatives in the area of post-quantum cryptography.
Good afternoon, respected attendees. Thanks, Aman, for the nice introduction. So my previous speakers have already spoken about post-quantum cryptography and quantum key distribution. And Atul has very well informed about the efforts being done in CDOT about quantum key distribution. So my talk is focusing on what things are being done in the area of post-quantum cryptography at CDOT. So just to have a brief background, as you all know that quantum computing has been of late in news, and lots of claims are being made of quantum supremacy, and lots of research is happening in the area of quantum computing and quantum algorithms, that this quantum computing and quantum algorithms are going to break the conventional cryptography. So all the efforts of CDOT in area of QKD and PQC are to ensure that secure communications are still there even in the presence of quantum computers. So this slide just shows that the experts are telling that quantum computing with quantum algorithms can lead to a crypto apocalypse type situation where all the security all the communication security gets destroyed. It is basically all the asymmetric cryptographic algorithms where there is a risk. And since asymmetric cryptographic algorithms have to be used along with the symmetric cryptographic algorithms for any practical security solutions, so it means the whole security infrastructure collapsing. So the key sectors which are impacted there include all the secure communications between business to business, business to consumers, business to government, government to consumers, government to government, and consumer to consumer. All your e-commerce, online banking, all are under threat. So it is important to take steps in time so that we do not face a crypto apocalypse type situation. The key objectives of post-quantum cryptography at C. are to provide future-proof cryptographic security in voice, data, and video communication through C. developed products, and to ensure that C. developed products keep pace and comply with the evolving PQC standards at international standard development organizations like NIST and ETSI. With these objectives, our PQC journey started in March 2018, that is somewhere here, and we did some study project in the area of to understand the post-quantum cryptography. We soon realized that there is a lots of theoretical mathematics involved with the newer post-quantum schemes, and therefore in February 2019, we had a consultancy agreement with academia to understand the nuances of the theory there. In June 2019, we came up with our first product, which is a layer 3 encryptor, which supports post-quantum cryptography key exchange. In September 2019, we further integrated this product with our Wi-Fi and Wi-Fi-based product like broadband wireless terminal and our routers. In November 2019, we had a presentation of our PQC work at ETSI IQC Quantum Safe International Conference, Cryptography Conference. And in January 2020, we started enhancing our VoIP phone product. So we have a CVP 200 named VoIP phone product, and we enhanced it to introduce quantum safe algorithms in the key exchange so that the signaling path remains protected. Thereafter, in February 2020, we did an integration of our layer 3 PQC encryptor with C.QKD prototype solution, which was done as per an ETSI specification, which was existing there, and so it is all as per ETSI standard that this integration was done. In March 2020, we initiated 2 new projects which were for NSCS, which are in the R&D of quantum secure smart video IP phone. Another product was post-quantum inline network encryptor. In November 2020, we also initiated a study with the Telecom Standards Development Society of India on post-quantum cryptography in 5G networks. And as Atul already mentioned, C. signed an MOU in April 2021 with the Institute of Development and Research in Banking Technology for exploring C. quantum safe products, which include post-quantum cryptography as well as QKD-based products in the banking and the financial sector. In the next few slides, I will just give you a brief about some of these products which are mentioned in this journey. So the first product which we came up with is a layer 3 PQC encryptor, or the compact encryption module. So this compact encryption module, it supports post-quantum cryptography key exchange algorithms. This product has 2 Ethernet interfaces, one plain and one cipher, and it is useful for secure cryptography data communication over internet across geographically distributed sites. This product supports up to 80 Mbps encrypted traffic. So when I say that the product supports post-quantum cryptography key exchange algorithms, so we are actually closely watching the NIST competition, and there are various categories of algorithms. As Professor Soumitra in his introductory presentation mentioned that there are lattice algorithms, there are code algorithms. So there are different categories of algorithms. So among the various categories of algorithms, we have added in our product the lattice and the code based, and these are the ones which are more prominent. And as the competition has evolved, we have tuned our product so that the algorithms which have passed to the later stages are there in our product. This is a use case scenario of a compact encryption module. So this can be used to connect to geographically distributed sites. So there are two machines across network, and they are in their individual LANs. And through compact encryption module, you can create an IPsec tunnel between them using post-quantum cryptography key exchange. And using those post-quantum cryptography exchange, and the symmetric keys get generated on both sides, and then AES 256, the standard symmetric encryption algorithm, is used for encryption. As Professor Sumitra pointed out, that symmetric encryption algorithms, the strength has been reduced to half by the developments in the Grover's algorithm. So it is recommended to use AES 256 and not AES 128. While the post-quantum cryptography key exchanges have to be totally by different newer methods, because the Shor's algorithm claims to have totally broken those. So the newer class of mathematics like lattice, the lattice algorithms, which Professor Sumitra mentioned in his presentation, and the coding theory-based algorithms are used in our product. This is another use case scenario. This is slightly different from the previous slide. This just shows that we have integrated our compact encryption module with the C.quantum key distribution solution as well. In this case, the two C.CMs will do a post-quantum key exchange using the post-quantum cryptography algorithms. In addition, they will take keys from QKD as well, and they will combine the two keys, and then the combined key will be used in the symmetric encryption algorithm. So the advantage of combining the QKD and PQC is to further enhance the security here. Then I just have one slide about this product which we are currently doing. This is a post-quantum inline network encryptor. So this product supports encryption, decryption of Ethernet and IP layer packet at 1 Gbps rate. It supports post-quantum key exchange. And the cryptographic operations here we are performing in FPGAs for better security and performance. And it is under a tamper-resistant enclosure. And the implementations are side channel analysis, attack-resistant implementations. So this product is a higher throughput as well as a higher, more secure version of our compact encryption module. And this supports all the post-quantum exchanges algorithms which are currently in the NIST competition in the most recent round. Then I just mentioned about post-quantum cryptography in C.VoIP phones. So C.Dot has a VoIP phone which is known as Sivp 200, and what we have done is we have enhanced the software of this phone. The advantage of working with C.Dot is that all the software and hardware aspects our teams are well versed with. So with the software of this product we have enhanced so that we have retrofitted the key exchange mechanisms in this with the PQC key exchange. And so now this product supports post-quantum cryptography key exchange and all the latest algorithms which are there in the NIST competition. Further, I just want to mention about another product which is currently under development and will be ready very shortly. So this product is a quantum secure smart video IP phone. So this product is you can consider as a more advanced version of the Sivp 200, which I mentioned in the previous slide. So this product has a touch screen and video interfaces, and the secure communication is built on post-quantum cryptography-based key exchange, and it has standard Ethernet and user access using biometric authentication and optionally face authentication, and it also has voice assistant and gesture control. So you see it has all the advanced features available in the commercial products, and even it has more advanced security in terms of post-quantum cryptography key exchange. This slide just shows how we protect the secure signaling path in a typical call establishment procedure of video IP phone. So you have these video IP phone on the left side. You have a SIP server and the associated servers required for call establishment on the right side. So this video IP phone will support post-quantum cryptography key exchange, and we have our compact encryptor module in front of the Sivp server, and so there is and this compact encryptor module and the Sivp server are co-located. So all these communications which take place, the signaling protocols communications between the phone and the Sivp server. So these get encrypted using post-quantum cryptography mechanism. So IPsec tunnel ensures that the post-quantum cryptography key exchange takes place between the phone and the encryptors. Further, as I mentioned that from CDOT, we have initiated study of post-quantum cryptography in 5G networks at TSDSI. The key motivation for this study is that, as we know, but many experts are strongly believing that quantum computers of such magnitude, which shall be a real threat to classical cryptography, shall be available in next 5 to 10 years. Now, this is within the life cycle of 5G networks, at least in India. So we see that also we know that in a few years from now, these 5G networks shall be prevalent in a lot of security sensitive verticals such as banking and finance, e-commerce, industrial IoT, and secure government networks. Well, if you look at the current 3GPP architecture for 5G, at a number of places between various virtual nodes, it has IPsec and TLS-based security tunnels that use classical public key cryptography. So we propose that this is a security risk considering the rapid advancements which are happening in the area of quantum computers. So the motivation of the study is to come out with the ways and techniques on which we can introduce quantum safe behavior in 5G. So this is till now what we have done in the PQC. What we plan in future is that first is we are planning to complete our quantum secure smart video IP phone, which will be very in a short time it's going to get completed. Then we have our Pine project that which I mentioned is a bigger capacity, more secure version of our post-quantum encryptor. And then we also plan to integrate with our CDOT's other flagship products where, for example, we want to make our DWDM systems PQC compliant. And when I'm saying PQC compliant, it means PQC as well as QKD compliant. Because PQC and QKD we have integrated, and that we want to use with the DWDM for the most enhanced security. And then we are also plan to develop even a higher version of our post-quantum inline network encryptor that can work up to 10 Gbps encryption or decryption throughput, PQC key exchange. And we want to include post-quantum cryptography as a part of security in our 5G or 6G networks, which the component which shall be developed by CDOT. So first of all, it's important that, which I mentioned, that PQC and QKD we have integrated, and we want to use this combined solution in enhancing the security of all our future products in future. Now, since we've been working in PQC for last few years, we have a complete understanding of ins and outs, and would like to use this platform for having enhanced security solutions in future for CDOT and for the country as such. Thank you very much. Any queries are most welcome.
Thank you, sir, for taking us through CDOT's cutting-edge R&D endeavors in the area of post-quantum cryptography. May I now request Dr. Pankaj Dalela, Director CDOT, for concluding the webinar and proposing the vote of thanks.
Hello, am I audible?
Yes, sir, you are audible, sir.
Yeah, so Dr. Rajkumar Upadhyay ji, ED CDOT, Professor Soumitra Kumar Sanadhya, IIT Jodhpur, Professor Anirban Patak, JIT Noida, speakers from CDOT, Sriyatul Gupta ji, Prashant Chugh ji, DOT officials, BSNL officials, DBNL, TCIL, ITI, TEC officers, academicians from various institutes, my fellow CDOTians, ladies and gentlemen, very good afternoon. It's indeed a great privilege and honor to produce vote of thanks for webinar on quantum communication to celebrate Azadi Ka Amrit Mahotsav 75 years of independence. It was a wonderful day as we listened to different experts in this field. Dr. Rajkumar Upadhyay, ED CDOT, has described how CDOT has taken the lead across the various products by applying this QKD and quantum-based solutions. And CDOT has already developed this QKD solutions and post-quantum cryptography solutions. And these are no more the lab models, but actually it is the industry-grade products. And we are providing the help to other industries in India for these solutions. So thank you, sir, for your valuable information. Professor Soumitra Kumar Sanadhya reviews various cryptographic algorithms. He has clearly stated the history and genesis of development of various algorithms, their limitations, along with current and future trends. History of quantum attacks models like Q0 to Q1 to Q2, then hard problem for quantum computers and need for quantum communication. Thank you, sir, for your valuable information. Professor Anirban Patak, he explained the theory behind the quantum communication, several aspects of quantum optics and quantum information with a focus on quantum cryptography, quantum logic gates, quantum teleportation, theory behind quantum key generation, and an Indian initiative in PRL and PRI, as per him, and he stated very correctly, we are late in comparison to China and other countries, but still we can catch the bus in the Atmanirbhar Bharat and secured India. And CDOT is also working in that direction. So QKD is not application, he said, rather it is utilized for secured communication. And he has also stated how Switzerland is using quantum cryptography for secured voting. He also discussed various components, that is circulator, etc., which is used for quantum secured channel. Thank you, sir, for your valuable information. Then our CDOT group head, optical division, Atul Kumar Gupta. He has clearly stated the product behind this, which is industry-grade product, quantum key distribution. And he has shown the data and he had the literature survey, like how the digital growth in data and the importance of security in transactions, dependency in major source of vulnerability due to malicious use, theft of data, and breach of privacy. He also presented quantum way of secured communication. He also said quantum mechanics also make it possible to easily break the current commonly used method of key generation and distribution. This is because advances in quantum communication and algorithm which can run on it. He also said that key generated by QKD can be mathematically proved to be secure, and security is not based on any assumptions or belief. That is why worldwide scientists and organizations are working on that. He also told that CDOT has already signed a memorandum of understanding with Physical Research Laboratory, part of ISRO Ahmedabad. That is the plan to integrate CDOT fiber-based QKD with PRL's free space and satellite-based QKD. This is to catch the bus in which we are behind with the Western countries. But I'm sure we will catch this bus and we will have a breakthrough in this field also. Then he also said that CDOT has signed MOU with the Institute of Development and Research in Banking Technology that is established by Reserve Bank of India. That is the plan to explore use cases of QKD in banking and financial services of service industry. And CDOT intend to play a key role in realization of goals and objectives set under QMNQTA. Quantum secured CDOT products has been informed, like the post-quantum cryptography, our encryptors and routers, all this has been described by Atul Gupta. Then with a wide range of indigenously developed communication products and solutions, CDOT is eminently poised as a trusted source of quantum secured end-to-end communication infrastructure. So thank you, Atul, for your valuable information. Then our next speaker, Sri Prashant Chugji, he described how this post-quantum cryptography encryptor module, which has been designed like from 80 Mbps to 1G, then he have a migration plans up to 10 Gbps. And he has shown that he has already taken this security certification from NIST and ETSI compliant agency. And he has shown the migration path of this applying application of PKC in 5G, 6G, and he has also participation in standardization for 5G application of PQC in TSTSI. Then he has shown the roadmap that how to be used their post-quantum cryptography solutions in 5G and 6G and DWDM systems and other different systems of the CDOT. Thank you, Prashant, for your valuable information. Then in the last, I thanks to all attendees from various institute and organization to make this webinar successful on the occasion of this Azadi Ka Mahotsav. Thank you very much everyone for attending this webinar and to make it a grand success. With this, I declare the completion of this webinar. Thank you. Jai Hind. Over to Aman, please. Thank you.
Thank you, sir, for giving us a lucid overview of conclusions and takeaways from CDOT's Azadi Ka Amrit Mahotsav webinar on quantum communications. Ladies and gentlemen, we hereby conclude the Azadi Ka Amrit Mahotsav webinar on quantum communications and thank all the speakers and participants for making this webinar a resounding success. Thank you all.
Thank you.